the United Nations Master Control Scheme. October 29, 2025. While you were occupied with your daily routines, an object comparable in size to Manhattan reached its closest proximity to our sun. It remained concealed, entirely undetectable from Earth. The timing of this event was remarkably precise, perhaps too precise. This was the exact moment a spacecraft would activate its engines for a course alteration, achieving peak efficiency and maximum energy acquisition. Furthermore, 3 weeks prior, the United Nations had initiated a worldwide surveillance initiative. On the very same day, SETI updated its protocols for interstellar contact for the first time in 15 years. All observational instruments focused on 3I 2025 U1, codenamed Oumuamua 2, with all systems synchronized. The crucial question is not whether something significant is occurring, but rather, what are they preparing for? If you find this narrative compelling, please engage the like button and subscribe to ensure you don't miss subsequent installments. Share in the comments section where you are engaging with this content and whether you perceive this timing as mere chance or a deliberate orchestration. Kindly share this video and activate the hype button to support our channel's growth. We appreciate your presence. Allow me to elaborate on a matter that should concern everyone attentive to Oumuamua 2. This concern extends beyond the object itself, though we will address that. It even surpasses the observed anomalies, such as the nickel emissions or the reversed tail. No, what should truly concern you is the sophisticated infrastructure that was established around this celestial body before the majority of the public was even aware of its existence. This infrastructure was meticulously designed for information management, to control what information reaches the populace, and to shape the prevailing narrative before any substantial content even existed to be managed. On September 30th, 2025, a white paper was presented to the United Nations Office for Outer Space Affairs. The esteemed authors of this document were Avi Loeb, Omal Dardai, and Gershon Tenenbaum. The paper strongly advocated for the coordination of global scientific research, maximizing observational coverage, and ensuring optimal monitoring of interstellar objects like Oumuamua 2. The rationale presented was that such objects could potentially pose a threat to humanity if they happened to be associated with extraterrestrial technology. The document stated, quote, "Black swan events with small probabilities must be considered seriously if their implications are large. This precisely captures the underlying sentiment and the presented framework." 3 weeks later, on October 21st, the International Asteroid Warning Network issued a public statement. They announced the commencement of a monitoring campaign for 3I 2025 U1, framing it as a training exercise for planetary defense. The designated period for this exercise was specific: November 27, 2025 through January 27, 2026. This time frame precisely encompasses the period when Oumuamua 2 will re-emerge from behind the sun, becoming observable once again. During this phase, any unusual activity, trajectory adjustments, or deployed objects would become detectable by Earth-based telescopes. On the same day, October 21st, the Minor Planet Center released an editorial notice. The notice, though technically dry and bureaucratic, highlighted the unique challenges that comets present for accurate astrometric measurements and orbital predictions. However, the timing of this notice, as with all these events, is noteworthy. And here is where the situation becomes particularly intriguing. In that same September, just prior to the submission of Loeb's white paper, SETI released a significant update. This update concerned revisions to their post-detection protocols, a project they had been developing for 15 years. These protocols outline the procedures to be followed upon the detection of extraterrestrial intelligence, specifically addressing who would be authorized to communicate, who would be informed, and who would control the dissemination of such a momentous message. The document itself is titled SETI Post-Detection Protocols: Progress Towards a New Version, with Michael Michaud listed as the lead author. Although the full research team comprised individuals from various international locations, the established framework effectively consolidates the authority for post-detection communication to a select group of authorized scientists, governmental bodies, and international organizations. Let us re-examine that critical phrase, a select group. The revision explicitly restricts individuals who can speak, who can share information, and ultimately, who can inform the world that humanity is not alone. On the surface, these initiatives appear to be distinct endeavors. The SETI protocols have been in development for an extended period. The International Asteroid Warning Networks campaign is a legitimate exercise in planetary defense. Professor Loeb's white paper represents academic advocacy. These are three seemingly unrelated initiatives from three separate organizations, all coincidentally converging in the same month and revolving around the same celestial object. However, let us carefully consider the operational structure that is being erected. SETI establishes the reporting policies, defining what constitutes a detection, the required evidentiary standards, and the prescribed communication channels. The International Asteroid Warning Network orchestrates the observational campaign, coordinating telescope arrays, data acquisition, and measurement procedures, thereby determining what is flagged as anomalous. At the apex of both these structures sits the United Nations Office for Outer Space Affairs, the sole entity where every national space agency already holds a recognized position. If one were intent on constructing a system to control information pertaining to an extraterrestrial object, this precisely describes the mechanism that would be implemented: a comprehensive information conduit. Data would flow upwards from telescopes worldwide, undergo filtration through the International Asteroid Warning Network's coordinated system, be processed according to SETI's established protocols, and subsequently be reviewed by the United Nations Office for Outer Space Affairs International Committee. Only after successfully navigating every layer of institutional scrutiny would such information be permitted to reach the public. The ingenious aspect, from a control standpoint, is that each individual step possesses a veneer of legitimacy. Planetary defense is undeniably a necessity. We require systems for tracking potentially hazardous objects. Post-detection protocols are indeed prudent. Establishing frameworks for first contact scenarios is essential. International coordination is paramount. Space is a shared global domain. No rational person would dispute these fundamental principles. However, when these elements are interconnected and their deployment is synchronized around a specific object, a distinct outcome emerges. A critical bottleneck is created, a singular pathway through which all information must invariably transit. And this is the chilling aspect that causes sleepless nights. This informational infrastructure was erected before Oumuamua 2 exhibited any unusual behavior. The white paper was submitted when the object was still 4 astronomical units from the Sun, preceding the reversal of its anti-tail, before its perihelion passage, and before any of the temporal coincidences that would later fuel speculation about its artificial origins. They constructed the information control system in anticipation of its necessity. Ponder this for a moment. Either they detected something within the data that has not been publicly disclosed, something that warranted the establishment of this framework before the object became front-page news, or they are conducting a comprehensive simulation, testing the system's capabilities using Oumuamua 2 as a convenient test case. Both scenarios are profoundly thought-provoking and raise critical questions that remain unaddressed by official channels. The original post that brought this matter to widespread attention articulates this perfectly. When I consistently spoke of a blanket of silence, this is precisely what I was referring to. If every anomaly must be reported through the same UN-sanctioned channel, then the entity controlling that pipeline dictates what is deemed factual, what is dismissed as rumor, and what the public is ultimately permitted to learn. Label it planetary defense, and no one would question it. You can construct a global sensor network, synchronize every major telescope, and monitor the skies around the clock without ever uttering the unsettling term UFO. And here lies the giveaway, the linguistic clue. Funding for planetary defense is readily available. It bypasses the need for lengthy hearings or sensational headlines, utilizing the identical infrastructure, but with a more reassuring designation. Would you seek funding for a global telescope array to search for extraterrestrial technology? You would likely face considerable challenges during congressional hearings. However, if you request funding for planetary defense against potentially hazardous asteroids, you are met with immediate budgetary approval, a clear mandate, and an established international coordination framework. The same hardware, the same sensors, the same data streams, merely presented under a different label. Yet, this infrastructure does more than just facilitate observation. It subjects us, the public, the very individuals funding these operations, to a form of testing. These so-called drills evaluate our collective response. They ascertain the speed at which a narrative propagates, identify individuals who challenge it, and determine which media outlets readily adopt the official language. This represents a stress test for the flow of information, extending far beyond mere asteroid tracking. When the dynamics of information flow are understood, it becomes equally clear how to obfuscate or manipulate it. This is an advanced strategy, the hallmark of contemporary information control. The objective is not to suppress a story outright, nor is it to classify everything and hope it remains buried. Such methods are no longer effective due to the proliferation of independent telescopes, the increasing number of amateur astronomers, and the multitude of individuals observing the skies. Instead, the approach involves establishing seemingly legitimate institutions, creating official channels, and instituting established protocols, procedures, and review boards. Subsequently, all information is meticulously funneled through these designated channels. The institution becomes the authoritative source, the entity that journalists contact for commentary, the repository where measurements are logged, and the committee responsible for differentiating between anomalous and normal phenomena. Should a genuinely unusual event transpire, such as Oumuamua 2 executing a maneuver, deploying auxiliary objects, or performing any action unexplainable as natural cometary activity, that information enters your established pipeline. It undergoes review by your committees, is contextualized according to your protocols, and by the time it reaches the public, it has been carefully shaped, framed, and managed. The rough edges are smoothed, the implications are meticulously worded, and the narrative is firmly controlled. This orchestrated process, of course, faces a potential disruption. An event so overt, so visible, and witnessed by too many individuals that it defies containment. This represents the ultimate nightmare scenario for any information control system, DJ. An event that completely bypasses the established pipeline. And this is precisely why the timing of this monitoring campaign is so critically important. The period from November 27th to January 27th coincides precisely with Oumuamua 2's emergence from solar conjunction, the time when amateur astronomers can again direct their telescopes towards it, and when any post-perihelion activity would become readily observable. The International Asteroid Warning Network campaign ensures that during this crucial interval, a coordinated global observation network is already in place, actively collecting data and feeding information through official channels. If an unusual phenomenon appears in the sky, if backyard telescopes begin detecting objects that were not previously present, the official network will also observe it, likely even before it is widely noticed given their superior resources. This allows the official narrative to be established before speculative theories take hold. It is, in a Machiavellian sense, a brilliant strategy. The aim is not to suppress information, nor is it truly to conceal anything. Rather, it is to ensure that when individuals seek authoritative information, when journalists require expert opinions, and when the public desires to understand unfolding events, they turn to these established sources. They trust the provided data and accept the presented framing because they are interacting with the International Asteroid Warning Network, the United Nations Office for Outer Space Affairs, or SETI, an organization with a decades-long history of searching for extraterrestrial intelligence. Whom else would they trust? Perhaps, just perhaps, this entire situation is precisely as it appears. Responsible scientific institutions undertaking responsible actions, developing frameworks for scenarios that, while improbable, are not impossible, coordinating observations of a rare and fascinating celestial object, testing their systems and procedures to ensure their efficacy should a genuinely hazardous entity emerge. It is possible that the timing is coincidental, that the synchronization is merely a manifestation of bureaucratic efficiency, with different organizations independently addressing the same challenge concurrently. However, there exists an additional dimension that warrants careful consideration: the psychological impact. These simulations, these monitoring campaigns, and these established protocols serve a purpose beyond their stated objectives. They normalize the concept of global cooperation in response to potentially threatening celestial objects. They instill in the public consciousness the understanding that such matters are taken seriously by governmental and international bodies, that established systems are in place, that vigilance is maintained, and that preparedness is a priority. And if the objective is to prepare the world for potential disclosure, for the possibility that humanity is not alone, that we are being visited, or that technologies exist within our solar system that we did not create, this is the method by which it would be achieved, not through a sudden press conference or a dramatic announcement, but through a gradual, incremental process. The infrastructure would be built first, establishing institutions, creating protocols, conducting drills, and gradually familiarizing the public with the notion that space agencies are monitoring unusual objects, that international cooperation is essential, and that certain events necessitate careful management and coordination. Consequently, when the actual event occurs, when something undeniably extraordinary manifests, the effort will not involve starting from scratch. It will not require the arduous task of building trust and establishing authority in the midst of a crisis. That preparatory work will have already been accomplished. The systems will be in place. The public will know whom to heed, and the narrative framework will already exist. However, the objective is not to prepare us for disclosure, but rather to manage it. This is the critical distinction. Information will inevitably surface, one way or another. There are simply too many eyes on the sky, too much data being collected by independent researchers, and far too many amateur astronomers equipped with sophisticated instruments. However, The control over how that information is disseminated, how it is interpreted, and what conclusions individuals draw from it is achievable. This is precisely what this established infrastructure enables. It is imperative to maintain a vigilant watch on this unfolding situation because, frankly, it raises significant concerns. The original post concludes with this assessment, and it is difficult to disagree. This is not based on definitive evidence of conspiracy or a deliberate cover-up, but rather on the discernible pattern, the striking coincidences in timing, the evident coordination, and the extraordinary implications that emerge when these factors are followed to their logical conclusion. The post posits that this entire affair has little to do with the object 3I 2025 U1 itself, and everything to do with control and financial considerations. Perhaps this assessment is entirely accurate. It might simply represent institutional power struggles, justifications for budget allocations, and bureaucratic empire building, all conveniently packaged around the intrigue of an interstellar object. Or, conversely, it is possible that they possess knowledge that has not yet been revealed to us. Perhaps the data they are acquiring, the measurements they are taking, and the signals they are detecting warrant this precise level of coordinated preparation. They may be constructing this infrastructure because they genuinely believe it will be necessary. We will soon discover the truth. The months of November and December will provide considerable insight, not solely concerning 3I 2025 U1 and its behavior as it emerges from behind the sun, but also regarding the operational mechanics of this system, the flow of information through these channels, the promptness of official statements, and the methods by which the narrative is shaped. We are no longer merely observing a celestial object. We are witnessing the real-time operation of an information control mechanism as it processes something genuinely unknown. NASA, in a selective shutdown, as reported by the Daily Mail on October 1st, 2025. The United States government has once again exhausted its funding. 15,000 NASA employees received notices of furlough, leading to the cessation of operations and the temporary deactivation of its websites. The space agency, widely recognized as America's premier institution for scientific achievement, officially ceased its operations. However, this closure was not absolute, particularly when critical matters arose. 2 days later, 3I 2025 U1 made its closest approach to Mars, a distance of 30 million kilometers. The Mars Reconnaissance Orbiter was strategically positioned, its high-rise camera capable of resolving objects as small as 30 centimeters from Martian orbit, offering a clear line of sight to the interstellar visitor. This presented a prime opportunity, the closest any human-made instrument would come to Oumuamua 2 during its entire trajectory through the inner solar system. This was the moment that could have revealed surface features, internal structure, and composition, providing crucial data to determine whether we were observing a comet or something entirely different. And yet, NASA was purportedly closed. This assertion, however, was contradicted by the Daily Mail. The tabloid publication, of all outlets, uncovered the discrepancy, placing NASA in an awkward predicament. When contacted for commentary regarding 3I 2025 U1, NASA maintained that the entirety of its space program was suspended due to the ongoing government shutdown and declined to provide further details. This was a standard, albeit bureaucratic response, an apology for being furloughed, and an invitation to revisit once Congress passed a budget. However, the Daily Mail observed something significant, something they subsequently published, which forced NASA into an uncomfortable position. If the agency was effectively shut down, why were selective announcements being made, such as the peculiar declaration of a mini-moon And why were briefings being disseminated? This selectivity was perceived as rather telling. Operations were apparently suspended only when it proved convenient. Consider this for a moment. During the very same shutdown that prevented NASA from commenting on 3I 2025 U1, from releasing high-resolution imagery, or from providing updates on one of the most significant interstellar visitors in recent history, the agency somehow managed to allocate resources to announce a mini-moon, a diminutive asteroid temporarily orbiting Earth. While certainly an interesting discovery and scientifically relevant, it hardly constituted an urgent matter, nor did it seem to justify breaking the silence imposed by the shutdown. The mini-moon announcement was disseminated through official channels, included direct quotes from NASA scientists, and featured accompanying graphics and orbital diagrams. It was a comprehensive press package, professionally produced and distributed, all while the agency was ostensibly inoperative. This occurred while they were apparently unable to spare resources to discuss an interstellar object exhibiting 8 documented anomalies. This exemplifies selective silence. This is information control in its most transparent form. A complete shutdown would have been too conspicuous. Releasing all information would have resulted in a loss of narrative control. Instead, a deliberate selection process was employed. Information deemed safe, mundane, and conducive to maintaining public interest in space exploration without raising unsettling questions was released. Simultaneously, information considered problematic, anomalous, or likely to generate speculation that the agency was unprepared to address was withheld. The high-resolution images undoubtedly exist. The Mars Reconnaissance Orbiter operates automatically, with its observation schedules planned months in advance. The spacecraft itself is unconcerned by government shutdowns. It dutifully executed its programmed observations of 3I 2025 U1 on October 3rd. The data was collected, and the images were transmitted to Earth, residing on servers awaiting processing, analysis, and a decision regarding their public release. However, NASA cannot release them at this juncture. Doing so would necessitate a determination of what the images reveal. If the images depict ordinary phenomena consistent with what one would expect from a natural comet, their release would be straightforward. The narrative would be simple. Here is what we observed. Here is its appearance. No complications, no surprises. However, if the images portray something unexpected, something that deviates from the established comet narrative, their release becomes considerably more complex. It would require extensive consultation, interagency coordination, and a carefully crafted messaging strategy before the images surfaced online and prompted public interpretation. The government shutdown serves as a perfect pretext for this delay. The justification: of course, we cannot release the data. Our personnel are furloughed. Processing is consequently delayed, with only essential personnel available. This explanation conveniently overlooks the fact that other data is being released and that selective operations are continuing. The shutdown acts as a shield, a rationale for withholding the most critical images of 3I 2025 U1 from public scrutiny. This situation is not confined to NASA. China's Tianwen-1 orbiter was also positioned to observe 3I 2025 U1 during its Mars flyby. China has released over 14,000 images from this mission, demonstrating a proactive approach to sharing its Mars data, showcasing its technological capabilities, and highlighting its achievements on the global stage. Yet, 3 weeks after the flyby, not a single image of 3I 2025 U1 has been released by Tianwen-1, nor has there been any official press release acknowledging an attempted observation. The silence from Beijing is profound and raises suspicions, particularly given that this is precisely the type of opportunity China typically seizes, view DJ, a chance to outperform NASA, to be the first to publish data, and to assert its space program's competitiveness and merit. If 3i 2025 U1 were merely a comet, and if the images revealed nothing unusual, China would have undoubtedly released them immediately, trumpeting their capture and contrasting it with NASA's perceived dysfunction. Their failure to do so suggests one of two possibilities. China's observation might have been unsuccessful, with their instruments failing to gather pertinent information. In such a scenario, it would be logical for them to publicly disclose this setback to explain the lack of results. Alternatively, they may have detected something requiring further deliberation, collaboration, or even communication with other international space organizations before determining the appropriate course of action. This particular pattern was promptly identified on Reddit with a discussion thread titled, "The Chinese silence on Three-Eyed Atlas is more concerning than NASA's," gaining traction within days of the celestial body's passage. The reasoning presented is sound. If Three-Eyed Atlas were a typical comet, China would likely have disseminated images immediately, aiming to overshadow NASA's release. The fact that they have remained silent, mirroring the reticence of American agencies, suggests that this object is not ordinary. It implies that the captured imagery contains elements that necessitate careful handling. Meanwhile, the European Space Agency, ESA, did indeed release images, albeit a limited and carefully curated selection from their ExoMars Trace Gas Orbiter. These visuals presented exactly what one would anticipate: a nondescript white dot, accompanied by a faint halo of gas and dust. There was nothing remarkable, nothing that would ignite widespread public interest or fuel speculative theories. These were, in essence, safe images VUDJ, the kind released when an entity wishes to project an image of transparency without divulging anything of genuine significance. However, the truly intriguing aspect lies in ESA's explicit acknowledgement of the limitations of their photographic capabilities. They stated that the instrument could not differentiate the nucleus from the surrounding coma because Three-Eyed Atlas was too distant, comparing the task of imaging its kilometer-wide nucleus to the impossibility of discerning a mobile phone on the moon from Earth. This serves as their official justification, the technical constraint they are using as a shield. Yet, this is not a genuine limitation, but rather a choice. The camera in question, Cassis, is designed for surface imaging and excels at capturing Martian terrain from close proximity. Employing it to observe a comet 30 million kilometers away is akin to using a microscope to examine distant mountain ranges. Clarity of fine detail is naturally impossible, resulting in a fuzzy image. The ExoMars Trace Gas Orbiter, however, is equipped with other instruments, including spectrometers and infrared sensors, specifically engineered to analyze distant objects, measure their composition, and detect anomalies. The critical question then becomes, why did ESA choose not to release spectroscopic data? Why did they refrain from discussing the findings from their other instruments? Why did they focus exclusively on the camera that was least suited for this particular observation? The answer lies in the safety of the camera's output. It presented a non-controversial image, confirming the established narrative surrounding the comet, without revealing anything that might contradict it. The alternative data, the spectroscopic and infrared readings, could potentially tell a different story. Therefore, they were not mentioned or discussed. Instead, the fuzzy image was released, and the matter was moved on. This exemplifies a strategy of information control in the contemporary era. It involves an appearance of transparency, with the release of data, the holding of press conferences, and the answering of questions, all while carefully managing what information is disseminated. safe revelations are prioritized, and the narrative is framed before external interpretations can take hold. Legitimate excuses, such as technical limitations, government shutdowns, or processing delays, are employed to explain the unavailability of more compelling data. A significant online platform brought this issue to the forefront, posing the pertinent question: who cares about the communication departments? We want to see the data from the scientists. This statement, appearing in numerous interviews, strikes at the core of the matter. It is not about scientists being unable to conduct their work due to a shutdown. Rather, it concerns communication departments, public affairs offices, and institutional review boards being unable to grant approval for releases. The data exists, and the scientists have indeed reviewed it. However, the institutional approval process is stalled, preventing any information from being made public. Consider the implications. NASA scientists are in possession of high-resolution images. They have processed and analyzed them, understanding the appearance of three-eyed Atlas at close range, yet they are unable to share this information. This restriction is not due to classification, but because the communication channels are effectively closed. The individuals responsible for authorizing disclosures are not functioning, and the system requires multiple layers of approval before any information can reach the public, layers that are currently inactive. This represents a form of information control achieved through bureaucratic processes and the standard operations of institutional machinery, rather than any overt conspiracy or cover-up. The standard review process, being sufficiently slow and cumbersome, ensures that by the time information is released, it is old news. The opportune moment has passed, the narrative has already been established, and any insights the data might have offered are buried beneath layers of context, interpretation, and official framing. However, there are occasions when the timing is too conspicuous to disregard, when the contradiction is too stark. This is precisely what the Daily Mail identified, forcing NASA into a precarious situation. It is untenable to claim a complete operational shutdown while simultaneously issuing press releases concerning mini-moons. One cannot simultaneously claim to be entirely inactive and selectively operational. If the agency were truly closed, no information would be released. If it were selectively operational, questions would inevitably arise regarding why some information flows while other is withheld. NASA opted for selective operation, choosing to maintain a public presence to sustain the space news cycle and prevent the very speculation that a complete information blackout would engender. In doing so, however, they inadvertently exposed their strategy. The release of information is a deliberate choice. Some narratives are prioritized while others are delayed, and these priorities are determined by criteria unknown to the public. What does it signify that three-eyed Atlas was relegated to a lower priority? What does it imply that during the most critical observational window of this object's journey through our solar system, at its closest approach to any human spacecraft, at the moment when its true appearance could finally be revealed, NASA chose silence, hid behind the shutdown, and allowed this opportunity to pass without public acknowledgement? It indicates that they are not prepared to disclose what they observed. It suggests that the images require further analysis, consultation, and time to formulate a coherent message. It implies that whatever the high-resolution imagery captured does not align with the natural comet explanation that has been the official stance from the outset. If the images were mundane, confirmatory, and precisely as expected, there would be no reason for delay, no reason to await the buildup of speculation while withholding data that could resolve the question. The longer the delay persists, the more suspect it becomes. Each day without a release suggests that the images are problematic, that they depict something unexpected, and that they require careful handling before they can be shared with a public increasingly skeptical of official pronouncements. This situation is only the beginning. Three-eyed Atlas is about to re-emerge from behind the sun. Amateur astronomers will once again direct their telescopes toward it. Independent observations will proliferate across social media. Should anything unusual manifest, should the object's behavior post-perihelion deviate from predictions, NASA's statements or silence will become irrelevant. The evidence will be available, images will circulate, and speculation will intensify. This is, unless, of course, official channels act first. Unless the International Wildlife Network, IWN campaign, captures the data. Unless the Coordinated Observation Network identifies it before amateur astronomers. Unless the information flows through the established channels meticulously constructed in September and October. The narrative will be set by authoritative sources, framed by institutions that people trust, and speculation will be managed before it escalates uncontrollably. This is the crux of the matter, the reason why the timing of the shutdown is significant, and why the selective silence is so revealing. They are buying time, preparing the ground, and ensuring that when information is eventually released, it will be through channels they control. This brings us to the claim made by an ESA whistleblower. On October 21, 2025, late in the evening Central European Time, a social media post appeared that fundamentally altered the situation. The author identified themselves as a space debris engineer, analyst at the European Space Agency. The language employed was technical, the details were specific, and the assertions were extraordinary. The post stated, "In mid-September, Fermi GST detected a stable signature on the object, which is not attributable to any other space source. In simpler terms, the object was emitting a continuous engine-like sound." Reread that. Engine-like sound. Not an intermittent burst or pulse, not the kind of emission expected from natural processes like outgassing or particle collisions, but a constant, stable signature indicative of something powered, active, and operating. The post went viral within hours, with screenshots circulating widely and analysis threads emerging across multiple platforms. The immediate questions were, is this legitimate? Is this individual genuinely an ESA employee? Is the Fermi data accurate? And if any of these claims hold true, why is this information emerging from an anonymous social media post rather than official channels? Let us dissect the claims. The Fermi Gamma Ray Space Telescope is indeed a real instrument, operational since 2008, continuously scanning the entire sky every 3 hours to map sources of high-energy radiation, including gamma rays and X-rays, the most energetic forms of light in the universe. Fermi detects pulsars, black holes, supernovae, active galactic nuclei, and other phenomena associated with cosmic violence and extreme physics. According to this purported whistleblower, it has also detected something emanating from Three-Eyed Atlas. The crucial point regarding Fermi data is its public accessibility. Every observation is archived, and every detection is cataloged. If Fermi truly identified an anomalous signal from Three-Eyed Atlas in mid-September, that data would exist in accessible databases, verifiable by researchers, and analyzable by amateur astronomers. This claim is falsifiable, rendering it either incredibly bold or remarkably foolish, depending on its veracity. The whistleblower further asserted, something big is about to happen. In December, many home-based observers will see it all. This is not vague speculation, but a specific prediction for December, coinciding with Three-Eyed Atlas's reappearance from behind the sun, when amateur telescopes will be able to observe it again, and whatever has been occurring during its hidden perihelion passage will become visible. The post further alleged a significant cover-up between ESA and NASA, involving top-secret data deliberately concealed from the public and even from fellow space agency analysts. The latter point is particularly significant, even from fellow analysts. This implies a compartmentalization of information within the agencies themselves, where only select individuals, teams, or clearance levels have access to the complete picture. Everyone else, including junior analysts, would be working with incomplete data. This is how genuine information security operates. Not everyone within an organization has access to all information. Information is segmented and compartmentalized, ensuring that no single person or team can comprehend the entire situation unless specifically authorized. This is standard practice for sensitive programs, and if dealing with something that could incite public panic or challenge fundamental assumptions, this is precisely how it would be managed. But why would an ESA engineer risk their career and potentially their freedom to anonymously post this information on social media? What is the motivation? Conscience? Fear? A belief that the public deserves to know? Or something else entirely? One circulating theory suggests this is not a genuine whistleblower, but a limited hangout, DJ, a controlled leak of information released intentionally through unofficial channels to gauge public reaction, test the waters, and assess how people respond to the idea that three-eyed Atlas might be artificial before any official statements are made. Intelligence agencies frequently employ such tactics. Float a story, observe its dissemination, measure the response, and adjust their strategy accordingly. If this is the case, it is a sophisticated operation. The details are specific enough to appear credible, but vague enough to avoid revealing classified information. The timeline is sufficiently near to convey urgency, but distant enough to allow for adjustments if the prediction proves inaccurate. Furthermore, the framing DJ, a concerned insider breaking ranks to warn the public DJ, is emotionally compelling, bypassing skepticism and fostering a desire to believe. However, let us assume, for a moment, that this is legitimate, that an ESA analyst has indeed encountered data convincing them that something extraordinary is occurring. What might that data look like? What could Fermi have detected that would warrant the description engine-like sound? Fermi does not actually detect sound, as space is a vacuum devoid of a medium for sound wave propagation. What Fermi detects is electromagnetic radiation in the gamma-ray spectrum, DJ high-energy photons. However, certain emission patterns can be metaphorically described as acoustic, regular, rhythmic, pulsed at consistent intervals. Pulsars, for instance, are often referred to as cosmic lighthouses, emitting radiation that sweeps across space like a clockwork beam. This type of signal could be metaphorically termed sound. Yet, pulsars are natural phenomena, rotating neutron stars with intense magnetic fields, bearing no artificial characteristics. So, what would an artificial signal resemble? What would prompt an analyst to describe it as engine-like? Stability would be paramount. Natural sources tend to fluctuate, varying in intensity and responding to environmental conditions. An engineered signal, conversely, would be consistent, locked to a specific frequency, maintained at a constant power level with no drift or variation, DJ. A signal that, upon observation, screams artificial. If three-eyed Atlas is indeed emitting such a signal, and if Fermi detected it in mid-September, this carries profound implications. Mid-September predates perihelion, the closest approach to the Sun, and any potential orbital maneuvers. The object was already active, powered, and operating whatever systems might be generating that signal. This contradicts a key tenet of the artificial hypothesis, which posited that if Three-Eyed Atlas were a spacecraft, it would wait until perihelion to execute major maneuvers for optimal efficiency and energy transfer. However, if it is radiating at gamma-ray energies a month before perihelion, it suggests continuous operation of active systems throughout its approach, not a dormant probe awaiting the opportune moment, but an active mission with ongoing power demands. What would necessitate such significant power expenditure? What systems would generate gamma-ray emissions? Several possibilities exist, none of them comforting. Accelerating matter to high velocities, operating a fusion reactor, or manipulating magnetic fields on an immense scale could all produce gamma rays as a byproduct. These are technologies we can conceptualize, but have not yet achieved DJ technologies, indicating capabilities far beyond our current engineering prowess. Alternatively, what we perceive as artificial could be a natural but exotic phenomenon viewed DJ, a novel cometary process previously unobserved, an interaction between the object and the solar wind generating high-energy radiation, or a phenomenon that mimics technological signatures without actually being technological. This is always the counter-argument, the more statistically probable explanation from a Bayesian perspective. We have observed thousands of comets. We have never encountered alien spacecraft. Prior probabilities hold significance. However, the whistleblower is not claiming the detection of gamma rays, but rather a stable signature inexplicable by any other known space source. This implies comparative analysis. Someone reviewed the catalog of known sources, phenomena, and natural processes and concluded that none matched Fermi's detection from Three-Eyed Atlas. This is a strong assertion, going beyond merely observing something unusual to actively ruling out alternatives, thus concluding, at least provisionally, that this is something novel. The December prediction introduces another dimension. Many home-based observers will see it all. What exactly will they see? If there is a gamma-ray signal, amateur telescopes cannot detect it. Specialized space-based instruments are required. So, what will be visible to ground-based observers that is not detectable in other spectra? One possibility is a trajectory deviation. If Three-Eyed Atlas executed a maneuver at perihelion, altering its velocity or direction in a manner inexplicable by gravitational forces, this discrepancy would become apparent as the object emerges from behind the sun. Astronomers plotting its position would immediately notice the deviation from predicted trajectories. This is something amateur observers could detect and independently verify. Another possibility involves debris. If Three-Eyed Atlas released smaller objects, deployed probes, or shed components, these would begin to separate from the main body as they follow slightly different trajectories. Over weeks and months, this separation would become visually apparent, with amateur telescopes detecting multiple objects where only one should exist. This would be unambiguous and impossible to attribute to natural causes. A third possibility is a change in the object's appearance itself. If an active system were radiating, engines were firing, or propulsion was visible in optical wavelengths, amateur observers would witness a comet that does not resemble a comet, behaving unlike any known comet, exhibiting clear signs of artificial activity. Any of these scenarios would be extraordinary, necessitating a complete reassessment of what Three-Eyed Atlas is, and all would be observable by the dispersed network of amateur astronomers who have been tracking this object since July. Such phenomena cannot be contained. The narrative cannot be managed. Once hundreds of independent observers begin posting images and data, with evidence originating from sources outside institutional control, the dynamic shifts. This is why the December timeline is significant and what the whistleblower might be hinting at. Not that ESA or NASA will unilaterally release information, but that the information will inevitably surface, irrespective of the agency's desires. The object's post-perihelion behavior will be so demonstrably anomalous that no amount of official explanation can sustain the natural comet narrative. However, we must acknowledge the inherent uncertainty. It is possible that this entire scenario is fabricated, a hoax, or misinformation. WDJ someone with technical expertise crafting a plausible story to attract attention. This occurs frequently, and the pattern is familiar. An anonymous insider, dramatic claims, and a prediction for the near future, set far enough ahead that by the time it fails to materialize, public attention will have shifted to other matters. The responsible approach is skepticism, a healthy dose of doubt, and waiting for confirmation for the data. We must wait for December to see if the prediction holds true. We should avoid becoming swept up in speculation based on an unverified social media post, however technically detailed it may sound. And yet, there is something compelling about the specificity. The reference to Fermi, the mid-September timeline, and the December prediction are all falsifiable claims. If someone is fabricating this, they have chosen verifiable details, providing the world with specific points to confirm or debunk. This suggests either extreme confidence or considerable recklessness. The scientific community is divided. Some researchers are diligently examining Fermi archives for any anomalous detections in the region of Three-Eyed Atlas during September. Others are dismissing the entire affair as an obvious fabrication. Most are waiting, observing, and contemplating whether December will bring vindication or embarrassment to the individual who posted the claim. What we do know is this: the public outcry was for good reason. It resonated with pre-existing skepticism, with existing distrust of official narratives, and with a growing frustration over the lack of openness surrounding Three-Eye Atlas. People desperately want to believe there's more to this saga. They want to believe that someone within the established order possesses the courage to challenge authority, to break ranks, and to reveal the truth about unfolding events. Whether this hope is warranted, whether this anonymous communique GC is genuine insider testimony or a meticulously crafted deception, we will not ascertain until December, when Three-Eye Atlas reappears from behind the sun. Only then, when we can re-aim our telescopes and observe firsthand any changes, will we know. The agonizing part is the waiting, the uncertainty, the palpable sense of anticipation that hangs in the air like the charged atmosphere before a thunderclap. Something momentous is on the horizon, or perhaps nothing will transpire, leaving us to feel rather foolish for having harbored the hope that, just possibly, this time, it was real. The perihelion window. October 29th, 2025. There are pivotal moments in the history of space exploration that redefine the boundaries of possibility. These are instances when celestial mechanics converge in ways that transform routine orbital paths into exceptional opportunities. October the 29th, 2025, was precisely such a moment. At an exact distance of 203 million kilometers from the Sun, Three-Eye Atlas reached its perihelion, its closest approach to the star, and its point of maximum velocity. This is the juncture where, if one intended to alter course efficiently, to optimize energy transfer, or to execute a maneuver with minimal propellant expenditure, action would be taken. This principle is known as the Oerth effect, named in honor of Hermann Oberth, a visionary in rocketry who understood that the most advantageous time to engage thrusters is when already moving at high speed, when deeply ensnared by a gravitational field, and when one's orbital velocity is at its peak. The physics involved can seem counterintuitive, One might logically assume that activating engines during periods of slow movement would be more efficient and controllable. However, this is not how orbital mechanics functions. When at perihelion, traversing at peak velocity, every meter per second of delta V you impart translates into a maximal change in kinetic energy. The mathematical principles are starkly clear. The energy augmentation is directly proportional to your velocity at the instant of thrust. Double your speed, and you double the energy transfer. Triple your speed, and you triple the gain. At perihelion, 3I Atlas was traveling at 68 kilometers per second. Engaging engines at this velocity ensures that every gram of propellant yields its utmost effect. Crucially, this optimal window occurred while 3I Atlas was obscured, entirely invisible from Earth. Solar conjunction had positioned it directly behind the Sun 8 days prior. No terrestrial telescope could detect it. No spacecraft orbiting Earth maintained a line of sight during those 8 days. From conjunction on October 21st through perihelion on October 29th, 3I Atlas operated in complete solitude. Whatever transpired during this period occurred without any witnesses. Was this mere chance? Avabe has relentlessly posed this very question in scholarly articles, interviews, and blog posts, meticulously examining the statistical improbability of this confluence of events. The object's trajectory brings it within tens of millions of kilometers of Mars, Venus, and Jupiter. This proximity is highly unusual. The probability is a mere 0.005%, representing a 5 in 10,000 chance, which is already unlikely. However, to compound this, perihelion occurring during solar conjunction, when Earth-based observation is impossible, adds another significant layer of improbability. If one were orchestrating a mission, if one were planning the course for an interstellar probe entering an alien solar system, and if one wished to conduct a significant maneuver without detection by the inhabitants of the third planet, this is precisely when such an operation would be performed, concealed behind their star, moving at maximum velocity, and positioned for optimal gravitational assistance. The timing is almost too perfect to be comfortable. Lois has assigned 3I Atlas a rating of 4 out of 10 on his scale of potential technological origins. This scale is quantifiable and specific, based on probability calculations for each observed anomaly. A score of 4 out of 10 may not sound substantial. It is less than half. However, within its context, it is extraordinary. Most celestial bodies register 0 points on this scale. Natural comets, asteroids, and all objects previously observed fall into this category. They are unequivocally natural, clearly gravitationally bound debris from planetary formation. 3I Atlas has accumulated 4 points through 8 distinct anomalies, 8 separate instances where it deviates from expected behavior for a random interstellar rock. These include its ecliptic alignment, the anti-tail that pointed sunward, the fortuitous timing of its arrival allowing close planetary encounters, its extreme nickel-to-iron ratio resembling industrial alloys, its nickel-to-cyanide ratio that is orders of magnitude higher than any known comet, its unusually low water content, its unprecedented negative polarization, and its trajectory origin within 9 degrees of the WOW signal's direction. Each anomaly, examined in isolation, can be explained. While unlikely, it is still within the realm of possibility. Natural processes can yield peculiar outcomes. Cometary chemistry is remarkably diverse. We have, to date, observed only 3 interstellar objects. Our sample size is exceptionally small. It is conceivable that 3I Atlas represents the typical diversity of interstellar objects, and our current expectations are simply miscalibrated. However, when 8 anomalies are considered collectively DJ, 8 separate ways this object diverges from the norm, 8 distinct improbabilities compounding. DJ statisticians begin to experience discomfort. It is at this point that a hypothesis, initially dismissed as absurd, starts to gain a degree of plausibility, not proven, not even probable, but possible enough to warrant serious investigation. And perihelion was the ultimate test, the moment of truth. If 3I Atlas is indeed artificial, if it is a probe, a spacecraft, or any technological entity not of human origin, perihelion was the time it would act, the moment it would leverage the Orth effect to perform the maneuver it had traveled so far to execute. What might such a maneuver entail? Several scenarios are conceivable, each carrying distinct implications. The most dramatic possibility would be a reverse Orth effect. This would involve firing engines in the opposite direction of motion to decelerate. Instead of traversing the solar system on a hyperbolic trajectory, the object would enter a bound orbit, effectively capturing itself. It would remain, becoming a permanent resident of this star system, rather than a transient visitor. The delta V required for such a maneuver is substantial. 3I Atlas was traveling at 44 kilometers per second upon entering the inner solar system. To slow down sufficiently for capture by the sun's gravity, it would need to shed a significant portion of that velocity, measured in tens of kilometers per second. This necessitates either a considerable fuel supply, an exceptionally efficient engine, or both. However, if such a maneuver were to be undertaken, perihelion would be the optimal moment to execute it, maximizing efficiency and minimizing fuel expenditure. Furthermore, timing it during solar conjunction would allow it to be performed without observation. By the time terrestrial observers could detect it again, the maneuver would be complete, its new orbit established, and it would already be proceeding on its post-capture trajectory. A second plausible scenario involves trajectory adjustment, not a complete capture, but a course correction. This would entail subtly altering its path to aim for a specific target, setting up a future encounter with a planet or moon. Such a maneuver would require considerably less delta V and would be far more subtle, making it harder to detect unless measurements were extremely precise. Nevertheless, it would eventually become apparent. As the object emerged from solar conjunction, and astronomers plotted its updated trajectory, they would notice it was not precisely where predictions indicated it should be. The deviation would be minor, but measurable and unexplainable by gravitational forces alone. A third possibility is deployment. This would involve releasing smaller objects, perhaps mini-probes or daughter craft, whatever terminology one prefers for technology not originating from humans. At perihelion, moving at maximum velocity, objects released from 3I Atlas would achieve maximum separation over time. Over weeks and months, they would diverge along slightly different trajectories, some directed towards inner planets, others towards outer planets, perhaps with some tasked with mapping the solar system in detail before the mothership continued its journey. This latter scenario causes considerable concern among some researchers. It presents not a single anomalous object to track and study, but multiple distributed objects following independent paths. Some of these objects might be small enough to evade detection for extended periods, essentially forming a fleet rather than an individual visitor. This fundamentally alters the challenge, rendering containment impossible. It implies that even if official channels manage to control information about 3I Atlas itself, they would be unable to control information regarding objects that separate and pursue their own courses. Lowe has been explicit regarding this possibility. If 3I Atlas is a colossal mothership, it will likely continue along its original gravitational path and eventually depart the solar system. The Earth maneuver might then be applicable to the mini-probes it releases at perihelion, targeting the planets within the solar system. This is the educated inference, the scenario consistent with engineering logic. Do not decelerate the large, valuable mothership. Allow it to pass through, gather data, and proceed onward while releasing expendable probes to collect detailed information from specific targets. The Sun's tidal forces would naturally separate objects released at perihelion. Variations in mass, size, and surface area relative to mass would cause them to respond differently to solar radiation pressure and gravitational gradients. Over a period of months, this separation would become dramatic. Objects initially meters apart could end up millions of kilometers apart. This natural dispersal ensures coverage and redundancy, creating multiple data-gathering platforms distributed across the inner solar system. And here lies the particular difficulty in confirming or denying this scenario. Small objects are notoriously hard to detect. Our asteroid survey systems are primarily designed to identify objects large enough to pose a threat to Earth, typically those hundreds of meters in diameter or larger. However, an object the size of a car, a bus, or even a small building is considerably more challenging to spot, especially if it reflects little light or is designed to be unobtrusive. We would not necessarily be aware if 3i Atlas had released anything at perihelion, not immediately, and certainly not unless we were observing with the appropriate instruments at the precise moment. And we were not observing. Solar conjunction rendered us blind. Whether by design or by coincidence, the most critical phase of 3i Atlas's passage occurred when we were incapable of observing it. Now we wait. We watch as the object emerges from behind the Sun in November and December, as amateur and professional telescopes reacquire it, and as precise positional measurements resume. We will then be able to reconstruct what transpired during the obscured interval. Trajectory analysis will reveal whether any maneuvers were executed. Multiple object tracking will determine if anything detached from the main body. Spectroscopy will indicate if the object's activity changed in ways inconsistent with natural outgassing. The data will eventually tell the story. Perhaps not the entire narrative, but enough to address certain questions. Did 3i Atlas follow purely gravitational dynamics through perihelion, or was its motion influenced by something else? This is a question that can be answered. It is measurable. It is the type of query that science is designed to resolve. However, there exists a shadow question underlying this measurable one. It is a question that cannot be answered through trajectory data or spectroscopic analysis. If 3i Atlas did maneuver, if it deployed objects, if it leveraged the Earth effect during its concealed passage, from whom was it hiding? Natural processes are indifferent to observers. Comets do not await solar conjunction to release gases. Asteroids do not time their orbits for privacy. Only an entity aware of being observed, an entity concerned with detection, an entity possessing intent, planning, and purpose would care about conducting critical operations during the sole window when Earth-based detection is impossible. That is the profound implication. That is what makes the timing so unsettling. Not merely that it is optimal from an engineering standpoint, but that it is also optimal from a strategic one, suggesting planning that takes into account the capabilities and limitations of Earth-based observation. 33 gigawatts of power struck the surface of 3i Atlas at perihelion. The solar illumination at that distance, focused on an object 5 kilometers in diameter, delivers more energy than 30 nuclear reactors. This represents available power, the energy a natural comet utilizes to sublimate ice, drive outgassing, and create the coma and tail we observe. However, it is also the energy a technological object could harness, use to operate systems, recharge batteries, and power any necessary operations. We tend to think of spacecraft as being power constrained. Our probes operate on minuscule nuclear batteries or modest solar panels, rationing every watt and meticulously budgeting their energy expenditure. But an object at perihelion, an object deliberately engineered to perform operations during its closest solar approach, possesses abundant power, more than sufficient for any reasonable engineering task. This is speculation built upon speculation. It involves taking tenuous evidence and constructing elaborate scenarios. Yet, this is the nature of confronting a mystery. When an object defies easy categorization, when its timing is too convenient to dismiss but too uncertain to confirm, imagination takes flight. We envision possibilities, sketch scenarios, and attempt to map the landscape of what might be true, even if we cannot definitively ascertain it. October 29th came and passed. 3I Atlas reached perihelion and continued on its path. From our vantage point on Earth, nothing overtly dramatic occurred. No explosions, no visible maneuvers, no apparent signs of artificial activity. The object remained hidden behind the sun, and we remained ignorant of whatever, if anything, transpired during those critical hours. However, the absence of evidence is not evidence of absence. We did not witness nothing happening. We saw nothing. Period. We were blind, and in that blindness, in that observational gap, possibilities multiplied, questions accumulated, and doubt flourished. The truth is embedded within the data we do not yet possess, within the high-resolution images yet to be released, within the trajectory measurements scheduled for November and December, and within the observations that the JUICE mission will capture. The truth is being meticulously determined at this very moment by instruments, databases, and scientists working through the evidence behind closed doors in space agencies worldwide. We are simply awaiting their disclosure of their findings, or perhaps what they are willing to reveal they have found, which may not be entirely the same thing. The anti-tail reversal mystery. Something changed between July and September. Something visible. Something documented. The tail of 3I Atlas, that plume of gas and dust that had been pointing toward the sun in the opposite direction, transformed. What was an anti-tail became a normal tail. What was anomalous became conventional. And the question echoing across the scientific community is, why? The Nordic Optical Telescope in the Canary Islands captured this transition. Its 2.5-meter diameter mirror, coupled with a patient observation campaign spanning months, provided a clear photographic record of 3I Atlas undergoing this transformation. The images are unambiguous. In July and August, the brightest emission from the object formed a fan-shaped structure pointing sunward. By September, that structure had reoriented itself. The dust and gas were streaming away from the sun, precisely as one would expect from normal cometary activity. David Jewett and Jane Liu, two of the most esteemed comet researchers in the field, published these observations. Their analysis is meticulous and technical. They note that the rate of mass loss from 3I Atlas scales approximately with solar radiation flux. As the object draws nearer to the sun, receiving more energy, it expels more material. This is standard cometary behavior. The dependency is consistent with carbon dioxide being the primary driver of its activity, as indicated by earlier spectroscopic analysis. Carbon dioxide sublimating from the surface, carrying dust particles along, creates the visible coma. There is nothing unusual about this in isolation, nothing that would typically raise eyebrows or generate headlines, except for the anti-tail, except for the fact that for 2 months, the brightest emission pointed in the wrong direction, contrary to the solar wind, contrary to radiation pressure. contrary to everything we understand about tail formation. Anti-tails are not unprecedented. They have been observed on solar system comets. However, they are almost invariably optical illusions, geometric artifacts. The tail is actually pointing away from the sun, as it should, but Earth's viewing angle makes it appear to point sunward. Changing one's perspective, or waiting a few days for orbital geometry to shift, resolves the illusion, revealing the tail in its expected position. But 3i Atlas presented a different scenario. Multiple observations from various angles confirmed that the anti-tail was genuine, not a perspective effect or an illusion. The dust was unequivocally moving sunward, against the forces that should propel it away. This necessitates an explanation, suggesting that something about the object's environment, composition, or behavior deviates from the standard model. Enter Loeb and Eric Quito, who proposed a detailed theoretical model. They posted their findings online, meticulously detailing the physics and explaining the transition from an anti-tail to a normal tail. Their model centers on ice sublimation rates. As 3i Atlas approaches the sun, its temperature increases exponentially, not linearly or gradually. Small changes in distance result in significant temperature increases, which in turn lead to even more substantial changes in the sublimation rate. At distances of 3 to 4 astronomical units from the sun, water ice fragments dominate the scattering signal. They are large enough, numerous enough, and reflective enough to be the primary visible component. But they possess short resonance times, meaning they do not persist long in the outflow, quickly sublimating or fragmenting. As the object draws closer and the temperature rises, the sublimation rate escalates sharply and the resonance time decreases. The ice fragments spend less time in view before disintegrating. Meanwhile, refractory dust particles, the rocky material that does not readily sublimate, persist. They endure longer in the outflow, accumulating. At closer distances, these dust particles become the dominant scatterers, what we observe. The object is no longer dominated by ice, but by dust. And dust interacts with radiation pressure differently than ice, forming normal tails that stream away from the sun. The model elegantly explains the observed transition, aligning with the timeline of observations. It provides a naturalistic explanation for what appeared anomalous. Problem solved, wouldn't you agree? The anti-tail was simply an unusual, yet explicable phase in 3i Atlas's evolution as it approached the sun. Nothing artificial involved, nothing requiring the invocation of technology or intentionality. However, Adam Hibbert, a colleague of Lowe's, offers an alternative interpretation. He posits that if 3i Atlas is an engineered spacecraft attempting to decelerate, this transition from an anti-tail to a normal tail near perihelion would precisely correspond to what one would expect from a shift between braking thrust and forward propulsion. Read that statement again. Let it fully register. A shift from braking to acceleration, a change in engine configuration, a spacecraft adjusting its maneuver based on its current velocity and its desired final state. This is what makes analyzing 3i Atlas so profoundly frustrating. Every observation lends itself to two interpretations. Every data point is consistent with both a natural explanation and the hypothesis of artificial origin. The anti-tail could be attributed to unusual ice sublimation dynamics, or it could be exhaust from a braking burn. The transition to a normal tail might be due to changing dust composition, or it could signify a switch from deceleration to acceleration mode. Both explanations are internally consistent and align with the observed data. Neither can be definitively disproven without additional information. This phenomenon is known in science as degeneracy, where multiple models can fit the same set of data. It is a common occurrence. Typically, Such puzzles are solved by acquiring more information, conducting more accurate measurements, and finding observations that clearly differentiate between competing theories. However, with the interstellar object Oumuamua, we face limitations. Our observations are confined to what we can capture from Earth's perspective, using our existing instruments during the brief periods the object is visible. We lack the ability to design the ideal experiment, control variables, or isolate specific factors. Consequently, we are left with uncertainty, facing two narratives that both appear credible. The choice between them hinges on prior probabilities. How likely is it that we are observing a natural comet with unusual but explainable characteristics versus the likelihood of encountering alien technology? The prevailing scientific consensus leans heavily towards the former, positing that natural explanations should always be favored unless definitively disproven by evidence. However, some researchers propose that we should not be so certain about our prior assumptions. We have only observed a handful of interstellar objects. This limited sample size does not provide sufficient information to understand the full spectrum of what might exist beyond our solar system. It is conceivable that interstellar comets exhibit extreme variability, that unusual chemical compositions are commonplace, or that phenomena that seem anomalous to us are in fact typical for objects formed in different stellar environments. Alternatively, it is possible that a fraction of these interstellar objects are not natural phenomena at all. Interstellar probes traversing the galaxy might be more prevalent than we imagine. We might be witnessing exactly what one would expect if technologically advanced civilizations are actively exploring their cosmic surroundings. Resolving this ambiguity requires empirical data rather than pure reasoning. Fortunately, a specific measurement exists that could definitively distinguish between natural and artificial origins: mass loss. If Oumuamua is indeed a comet shedding dust and gas naturally, there should be a direct correlation between the quantity of material expelled and the observed brightness of its tail. Increased mass loss would translate to more visible particles, resulting in a brighter tail. This relationship is quantifiable and testable. Observations indicated that Oumuamua shed approximately 2 million tons of material between July and October. While this quantity seems substantial, it is insignificant compared to the object's total estimated mass, which exceeds 33 billion tons. The 2 million tons represent a mere 0.00005% of the total mass of UDJ, essentially negligible, a mere rounding error. To provide context, the observed outgassing would require ablating a surface layer with an average thickness of 4 centimeters. This 4 centimeters, compared to the object's 5-kilometer width, is akin to the ratio between the length of your palm and the length of Manhattan Island. This analogy perfectly captures our limited understanding. We have observed the object's surface, its outer layer, but have no insight into its interior. Inferring the internal composition of an object from just 4 centimeters of ablated surface material is impossible. We cannot determine whether it comprises ice, rock, metal, or something entirely different. The observed outgassing could originate from surface volatiles unrelated to the bulk composition. The tail's appearance might reflect deposited materials rather than the object's fundamental makeup. This distinction is critical and explains why the mass loss data does not definitively settle the question. Yes, we observed cometary activity, and yes, the object shed gas and dust in a manner consistent with a natural comet. However, this surface activity only confirms that the exterior behaves as expected if it is coated with ices and dust. It does not prove the entire object is natural. The composition of its interior, the bulk of its mass, remains unknown. A technological artifact traversing our solar system would naturally accumulate surface ices over millions of years of interstellar travel, drifting through molecular clouds and encountering trace gases and particles. This accumulation would form a coating. When such an object approaches a star, solar heating would cause this coating to sublimate, mimicking the appearance of a comet. The exterior would behave naturally, even if the interior were artificial. This represents a stealth characteristic, making it potentially more challenging than anticipated to differentiate between natural and artificial interstellar objects. If an advanced civilization intended to dispatch probes to other star systems undetected, encasing them in icy material would be an intelligent engineering strategy, VDJ natural camouflage. Such objects would resemble typical interstellar icebergs until subjected to close scrutiny, revealing anomalies. Oumuamua indeed presented anomalies, DJ8 in total. Individually, these were statistically unlikely, but not impossible occurrences. Collectively, however, they painted a picture that is increasingly difficult to dismiss. The presence of an anti-tail was one such anomaly. While not the strongest piece of evidence, nor a definitive smoking gun, it was an additional data point that did not quite fit, providing another reason for closer examination and suggesting that this object warrants more scrutiny than a typical comet. The reversal from an anti-tail to a conventional tail does not alter this assessment. It actually enhances the intrigue. We now have documented behavioral changes, an object that exhibited one behavior and then transitioned to another. The timing of this transition, coinciding with its approach to perihelion and entry into an optimal window for potential maneuvers, raises questions. Did the object change due to evolving physical conditions, VDJ increased temperature, altered sublimation dynamics, or the dominance of different materials in the outflow? This is the natural explanation, as described by the models proposed by Lowe and Quito, and it is likely correct, or at least probable. Or, did the object alter its behavior because its operational mode changed? Perhaps it completed a braking phase and transitioned to a different configuration, or its mission profile necessitated distinct thrust profiles at different points along its trajectory. This latter explanation ventures into speculation and is almost certainly incorrect. However, the gap between probably and almost certainly is where the most compelling questions reside. It is within this uncertainty that speculation thrives, and where we are compelled to acknowledge our insufficient knowledge for absolute certainty. This acknowledgement of uncertainty can be uncomfortable for scientists accustomed to confidently explaining phenomena, relying on functional models, and finding natural explanations to be sufficient. Oumuamua challenges this confidence, not with definitive, unambiguous evidence, but persistently, repeatedly, with a succession of anomalies, with timing that appears too convenient, with behavior that is too unusual, and with observations that consistently generate alternative interpretations, even when natural explanations are available. The images captured by the Nordic Optical Telescope are aesthetically pleasing and scientifically valuable, documenting a transition that offers crucial insights into how interstellar comets evolve as they approach a star. The analyses by DeWitt and Liu are robust, and the model proposed by Lowe and Quito is sophisticated. This represents sound scientific practice, observation, analysis, theoretical explanation, and publication of results, VDJ. Precisely the process we aim for. Yet, beneath the meticulous measurements and complex mathematical models, there is an undercurrent of unease, of DJ, a sense that we might be explaining what we can measure while overlooking what truly matters. It is possible that the surface phenomena we observe are distracting us from deeper questions about the object's true nature. 4 centimeters. That is the extent of the material ablated during 3 months of observation. the palm of your hand versus Manhattan Island. We are forming judgments about the entire object based on this minuscule sample, on its outermost layer, on what solar heat stripped away during its approach. What lies beneath remains concealed. The bulk of its mass is unknown. What transpires internally, if anything, remains speculative. We have examined the skin, but not the body. Until we do, until we obtain more comprehensive data, more precise measurements, and closer observations, the question persists. Is Oumuamua a comet, or is it masquerading as one? The reversal of its tail does not provide an answer. It merely adds another piece to an increasingly complex puzzle. The missions Europa Clipper and Hera, with their eye-on-tail passage capabilities, represent an accidental opportunity. Sometimes, circumstances align in ways that were unplanned, but can be exploited by all. Between October 30th and November 6th, 2 spacecraft on entirely unrelated missions were fortuitously positioned to traverse the ion tail of Oumuamua. This was not a deliberate design choice, nor was it predicted when these missions were conceived years ago. Instead, orbital mechanics occasionally creates such serendipitous alignments. Europa Clipper, launched recently towards Jupiter, is tasked with studying icy moons and searching for conditions conducive to life beneath their frozen surfaces. Hera, on its trajectory towards a binary asteroid system, is part of humanity's inaugural planetary defense initiative. Neither mission was conceived with Oumuamua in mind, nor were they designed to study comets. Yet both found themselves in the opportune location and time to sample material ejected from the most enigmatic object to visit our solar system in years. The physics governing cometary ion tails are straightforward. The solar wind, a continuous stream of charged particles emanating from the sun, interacts with the coma surrounding the comet. Molecules become ionized, losing electrons. This leaves behind charged atoms, ions, which are influenced by magnetic fields. The solar wind carries its own magnetic field, which then drags these ions along. Their trajectory is not a direct line backward from the comet, but is curved, following the intricate topology of the interplanetary magnetic field. Precisely predicting the final destination of these ions is complex, requiring knowledge of solar wind speed, magnetic field strength, and the rate of ion production by the comet BUDJ, all of which fluctuate based on changing conditions. Nevertheless, estimations can be made, probable paths calculated, and potential spacecraft intercepts with the tail determined. 2 researchers, Grant and Jones, undertook this precise calculation for Oumuamua. They mapped the expected trajectory of its ion tail and cross-referenced it with the positions of spacecraft in the inner solar system. Their findings indicated that both Europa Clipper and Hera would pass through regions where ions from Oumuamua were anticipated to be present. While not directly through the densest part of the tail, they would be within 8 million kilometers of the central trajectory, a distance that, while vast, is within the immense spread of ion tails from active comets, which can span millions of kilometers in width and tens of millions in length. The ions, though sparse and widely dispersed, are detectable with the appropriate instruments, and Europa Clipper possesses such capabilities. Its plasma instrument is designed to measure charged particles around Jupiter's moons, and its magnetometer can detect magnetic field variations. Both instruments are capable of identifying the signature of cometary ions should the spacecraft encounter them. Hera, unfortunately, lacks the necessary equipment. Its instruments are optimized for studying asteroid surfaces and composition, rendering it incapable of detecting ions or measuring magnetic fields with the required precision. Consequently, even if Hera traverses the densest portion of Oumuamua's tail, it will remain unaware, unable to collect usable data. The opportunity will pass unnoticed by its sensors. Europa Clipper, however, is different. It can detect and measure ion densities, identify specific species, and track magnetic field draping (VDJ), the phenomenon where magnetic field lines wrap around an obstacle like the comet, similar to water flowing around a rock. This pattern is distinctive and easily distinguishable from the background solar wind structure. If Europa Clipper flies through Oumuamua's ion tail, provided the timing and trajectory align perfectly, it will observe this draping signature and detect ions that should not be present in interplanetary space far from any apparent source. These ions will convey a narrative, revealing the composition of Oumuamua, the substances sublimating from its surface, and the chemicals present in concentrations sufficient to generate detectable ion populations. This is significant because we still lack definitive compositional data. Spectroscopy has provided clues. Carbon dioxide appears dominant, water is present but surprisingly scarce, and nickel compounds exhibit unusual ratios. However, spectroscopic analysis from Earth-based telescopes is limited by atmospheric interference, the vast distances involved, and the analysis of faint signals against noisy backgrounds. Direct sampling offers a distinct advantage. If Europa Clipper's instruments measure ions originating from Oumuamua, this constitutes in situ data of DJ direct detection, the gold standard for compositional analysis. Instead of inferring potential constituents from spectral lines, scientists will be counting actual atoms, measuring actual abundances, and obtaining ground truth. What makes this particularly valuable is that ion tails sample different material than dust tails. Dust consists of heavier particles, too large to be efficiently ionized, such as rocky grains and organic compounds that reflect sunlight and form the visible tail. Ions, conversely, are lighter elements, volatiles that sublimate easily and are stripped of electrons by solar radiation. Elements like hydrogen, oxygen, carbon, nitrogen, and sulfur (VDJ). The fundamental building blocks of chemistry (VDJ) can reveal information about the object's formation environment. If Oumuamua originated in a molecular cloud around another star and has traversed interstellar space for millions or billions of years, its composition should reflect this history. Isotope ratios might deviate from solar system values. Elemental abundances could bear signatures of different stellar nucleosynthesis processes, and specific chemical species might be present that are not found in our native comets. Any of these discoveries would be scientifically exhilarating, offering new insights into planetary formation in other stellar systems. Alternatively, if certain elements appear in ratios inconsistent with natural processes, or if the chemistry suggests deliberate engineering rather than natural evolution, this would be equally, if not more, exciting, prompting a re-evaluation of our current understanding of the object. The window between October 30th and November 6th is narrow, lasting only a week. This is the duration Europa Clipper will spend in the region where Oumuamua's ions might be present. The spacecraft is traveling at high speed, approximately 30 kilometers per second relative to the Sun, on its journey to Jupiter. It is not slowing down or maneuvering to optimize its passage through the tail. It is simply transiting the area, and the outcome will depend on whether it detects anything. The primary challenge lies in sensitivity. Cometary ions are sparse, even more so 8 million kilometers from the tail's axis. Detecting them requires instruments operating at peak performance, meticulous data analysis, and a clear understanding of what to look for and how to differentiate it from background noise. Europa Clipper's plasma instrument is advanced, designed for the harsh radiation environment around Jupiter and capable of detecting faint ion populations in the magnetospheres of icy moons. However, It has never been tested on cometary ions, nor calibrated for such measurements. The team will need to exert considerable effort to extract meaningful signals from the noise and confirm that any detected ions genuinely originated from Oumuamua and not from another source. This process takes time. Data is downloaded from the spacecraft, processed, analyzed by teams of scientists who compare it to models and predictions, undergoes peer review, and is eventually published in scientific journals. Typically, this entire process, from detection to publication, spans months, sometimes years. Therefore, even if Europa Clipper detected Oumuamua's ions in early November, we might not learn about it until well into 2026, unless the signal is exceptionally dramatic, unambiguous, or sufficiently unusual to warrant immediate attention. In such a scenario, a preliminary announcement might be made, or perhaps someone might bypass protocol and share results before full analysis is complete, deeming the data too compelling to withhold. However, it is more probable that the process will unfold conventionally. Data will be collected, analyzed, and eventually published. By the time we read about it in a scientific journal, Oumuamua will have long departed, continuing its journey back towards interstellar space beyond Jupiter. The window for follow-up observations will have closed, and the opportunity to gather additional data will be lost. This is the inherent frustration of studying transient phenomena. We get a single opportunity to make measurements. If our instruments are not perfectly calibrated, if our timing is slightly off, or if conditions are not optimal, we miss the chance. And with interstellar visitors, there is no opportunity for a subsequent attempt. By the time we design, construct, and launch a probe to intercept an interstellar object, it will be long gone. Consequently, we must utilize the resources we have, the assets already in space, the missions currently underway, and the fortuitous opportunities that orbital mechanics occasionally provides. Europa Clipper was not originally intended to study Oumuamua, but it will now do so. Whether this study yields valuable data depends on factors beyond our control: the solar wind conditions during the passage, the performance of the instruments during those critical days, and the actual density and distribution of ions in the tail. We will not know until the data is returned, analyzed, and shared with the scientific community. Until then, our only recourse is to wait and hope that fortune favors us, that the trajectory alignment was sufficiently precise, that the instruments were sensitive enough, that the tail was dense enough, and that all the necessary factors converged favorably. There is a certain poetic resonance in this scenario. Humanity's most advanced mission, designed to search for extraterrestrial life, even if it's microbial life beneath ice, inadvertently encountering material from an object that could, however improbably, be artificial. Europa Clipper is actively seeking biological signatures, investigating chemical markers of metabolism, and hunting for conditions that might support living systems. In parallel, it is passing through the exhaust plume of Oumuamua. If both possibilities hold true, VUDJ. If Europa is indeed habitable and Oumuamua is artificial VUDJ, then Europa Clipper inadvertently connects them, bridging the search for natural life with the possibility of technological life, and drawing a parallel between two vastly different approaches to answering the fundamental question of our solitude in the universe. One involves searching for simple cells in dark oceans, while the other involves stumbling upon the engineering of another civilization. Most likely, neither scenario will prove true. Europa is probably sterile, and Oumuamua is almost certainly a comet. Consequently, Europa Clipper's passage through its tail will likely yield interesting but ultimately unremarkable compositional data. Carbon dioxide, water, and trace organics in proportions consistent with our expectations. Nothing revolutionary, Nothing that fundamentally alters our understanding, merely another data point in the catalog of interstellar visitor compositions. However, there exists a small, non-zero probability that the data from Europa Clipper will surprise us. It might reveal chemistry that defies natural explanation, signatures that cannot be readily accounted for by natural processes, forcing us to consider possibilities we have hitherto avoided. Should this occur, and if preliminary results leak before formal publication, revealing something that demands immediate attention, we could know within weeks. Someone will speak. Someone always speaks. When the data is truly remarkable, someone will confide in a colleague who shares with another colleague who then posts anonymously on the internet. The scientific community is prone to leaks when the stakes are sufficiently elevated. Therefore, we observe, we listen, we monitor the various channels through which information flows, both official and unofficial. We anticipate a signal indicating something significant has been detected, or we await silence, which likely signifies that nothing out of the ordinary was discovered. In either scenario, the Europa Clipper's passage through the ion tail of the object presents another test, another chance for 3I Atlas to reveal its true character, another opportunity for us to gain insight into what this celestial body truly is. The spacecraft made its transit in early November. The data has been recorded. The truth has already been established, residing in computer memory somewhere, awaiting analysis. We are simply unaware of it at this moment. We do not know what Europa Clipper observed. We do not know whether the ion tail concealed mysteries or merely reflected ordinary chemical processes. But eventually, we will, when someone undertakes the analysis of those specific data sets, when someone identifies an unexpected pattern or confirms a prior assumption, when someone determines that the findings are ready for dissemination. Until then, we remain in a state of suspense. We know the measurement was taken, but we do not know what it revealed. We are waiting for information that already exists, but has not yet reached us. This is our current predicament concerning 3I Atlas across numerous fronts. Data exists that we cannot access. Measurements have been taken that have not been shared. Images have been captured that have not been made public. The truth is out there somewhere, residing in databases, file systems, and analysts' workstations. However, it has not yet reached the public. It has not reached the individuals posing the questions. It has not reached those of us striving to comprehend the nature of this object. The Europa Clipper's passage is merely another component of this intricate puzzle, another measurement that may or may not yield significant information, another chance that might or might not prove fruitful, another avenue to explore in the hope of unraveling the enigma. The observation window for JUICE commenced on November 4th, specifically November 4th, 2025. ESA's Jupiter Icy Moons Explorer passed within 64 million kilometers of 3I Atlas. This is not an exceptionally close proximity by astronomical standards. It remains distant enough that discerning significant detail would be impossible even with superior optics, yet close enough to facilitate measurements. It was close enough to gather data that terrestrial telescopes are incapable of collecting. It was sufficiently near to be meaningful. JUICE was launched in April of 2023. It has been in transit for over 2 years, gradually increasing its velocity through gravitational assists, making its way towards Jupiter, where it is slated to spend several years studying Ganymede, Callisto, and Europa. The mission's timeline is extensive. The spacecraft is not expected to enter Jupiter's orbit until 2030. Every aspect of the JUICE mission is characterized by patience and meticulous planning, designed for the protracted journey of deep space exploration. However, on November 4th, JUICE experienced a brief encounter with something unforeseen, something that was not accounted for in the mission plan at the time the spacecraft was conceived. 3I Atlas did not exist when JUICE was launched. It was only discovered in July of 2025. By the time the existence of this interstellar visitor traversing the solar system was known, JUICE was already en route, its trajectory predetermined, its observation schedule meticulously planned years in advance. Nevertheless, an individual at ESA reviewed the trajectories, performed the necessary calculations, and realized that JUICE would pass relatively near 3I Atlas merely days after perihelion. This presented an opportunity deemed worthy of pursuit, warranting adjustments to schedules and the dedication of spacecraft resources to observe an object entirely unrelated to Jupiter's icy moons. That decision conveys a significant message. It indicates that ESA regards 3I Atlas as sufficiently important to modify an exceedingly costly interplanetary mission, important enough to expend fuel, time, and instrument operational capacity on a target that was not part of the original plan. Important enough to justify the inherent risk, however minor, of introducing added complexity to an already intricate mission. Space agencies do not undertake such decisions lightly. Every orbital maneuver incurs fuel expenditure. Every activation of an instrument consumes power. Every unscheduled observation represents time diverted from pre-planned objectives. Mission teams are highly protective of their resources. They actively resist the tendency for mission scope to expand. They push back against requests to observe opportunistic targets unless the target possesses genuine scientific significance, unless the potential scientific return adequately compensates for the expenditure. ESA determined that 3I Atlas met that critical threshold. This operational decision reveals their internal assessment of the object. Regardless of their public pronouncements or how they frame the matter in press releases, their actions speak volumes about their evaluation. This object warrants observation. It merits resource allocation. This is precisely why the observation on November 4th took place. It occurred a mere 6 days subsequent to perihelion, 6 days after 3 Atlas achieved its closest approach to the Sun, 6 days after the optimal period for any hypothetical maneuvers. This timing is of paramount importance. If any alterations occurred during perihelion, if the object underwent any transformations or released any components or modified its trajectory, these changes would likely become apparent by November 4th. Solar tidal forces would be acting upon anything released at perihelion. Different masses, following marginally distinct paths, would begin to separate after a 6-day interval. This separation could be measurable, potentially manifesting in imaging data as multiple objects where only one was expected, or appearing in spectroscopic analysis as distinct emission signatures originating from different locations. Conversely, if no unusual activity transpired, if 3I Atlas behaved precisely like a natural comet during its perihelion passage, then the November 4th observations would serve to confirm this, revealing a single object on a predictable trajectory with activity levels consistent with solar heating. This would provide the definitive data point indicating that the behavior was normal. It was explicable. It was not anomalous, despite all the prevailing speculation. Either outcome carries substantial value. In either case, JUICE's observations will contribute to narrowing the possibilities regarding what transpired during those concealed days when 3I Atlas was obscured by the Sun. They will help refine the range of potential explanations. They will assist in answering questions that cannot be addressed from Earth's vantage point. However, there is a significant caveat. The data will not be released until February of 2026, a full 3 months after the observation itself. This 3-month period is allocated for processing, analysis, and review, during which the science team will meticulously examine what JUICE observed, ascertain its meaning, and determine the most appropriate method of presentation. The reason for this delay is distance. JUICE is positioned far from Earth. Communication with the spacecraft is time-consuming. Data downlink rates are considerably slower compared to satellites in Earth's orbit. The antennas of the Deep Space Network, responsible for receiving signals from interplanetary spacecraft, are shared resources with time allocated among multiple missions. JUICE receives its designated communication windows, and data trickles back. It then enters queues for processing and awaits its turn. This is standard procedure for deep space missions. No one anticipates immediate results. The mission teams are accustomed to working with delayed data, with observations that occur weeks or even months before they have access to the actual measurements. This is an inherent part of the endeavor, a fundamental rhythm of interplanetary exploration. However, for those of us closely following 3E Atlas, for those attempting to decipher the nature of this object, a 3-month delay can feel like an eternity. This is a period during which the object continues its outward journey from the Sun, a period during which its observation from Earth becomes increasingly challenging. It is a period during which any events that may have occurred at perihelion become significantly more difficult to verify or refute. By February of 2026, 3I Atlas will have journeyed far beyond Earth's orbit, continuing its outward trajectory, its visibility diminishing as its distance from the Sun increases. While still observable with powerful telescopes, it will no longer present the bright, active spectacle it did during its close approach. The window for detailed scientific study will be narrowing, and we will only just be receiving the JUICE data that could illuminate what we may have missed. Unless an extraordinary circumstance compels an early release, unless JUICE observes something so unusual, so unexpected, so profoundly important that ESA deems it impossible to withhold the information for 3 months. In such a rare instance, we might anticipate a preliminary announcement, perhaps a mention of unexpected findings at a scientific conference, possibly a press release that deviates from the standard timeline, but it is highly probable that ESA will adhere to their established schedule, processing the data rigorously, allowing the science team to conduct their analysis without undue pressure, and publishing the results only when they are fully prepared, not prematurely. This represents the responsible conduct of space agencies. This is the professional approach, even when there is an overwhelming collective desire for immediate answers. Therefore, the pertinent question is, what will JUICE observe? What instruments will be employed for this particular observation? The spacecraft is equipped with 11 scientific instruments, including cameras for optical and infrared imaging, spectrometers for analyzing composition, magnetometers and particle detectors for characterizing the space environment, and radar for subsurface probing, although the latter would be of no utility for observing a cometary object. The imaging system is likely to be the primary instrument for the 3I Atlas observation. Janus, the optical camera, is capable of capturing images across visible and near-infrared wavelengths. While designed for photographing the surfaces of icy moons from orbit, it functions effectively for observing distant cometary bodies. The resolution, at a distance of 64 million kilometers, will not be exceptionally high. Surface features will not be discernible, but it will be possible to measure brightness, track the object's position, and identify any extended structures within the coma. The spectrometers hold potentially greater interest. MAGIS, the infrared spectrometer, can identify molecular species present in the coma, measure temperature, and detect absorption features that indicate which ices are undergoing sublimation. If 3I Atlas exhibits unusual chemical composition, if those nickel compounds are present in concentrations suggested by ground-based spectroscopic analysis, MAGIS should be able to detect them, providing a stronger signal, clearer spectra, and a more definitive identification than terrestrial instruments were able to achieve. The ultraviolet spectrograph, UVS, operates at shorter wavelengths. It captures ultraviolet light that is absorbed by Earth's atmosphere, rendering it unobservable from ground-based telescopes. Ultraviolet spectroscopy reveals different molecular species, distinct chemical processes, and unique physical interactions. It provides a complementary perspective that adds information which optical spectroscopy might miss. In conjunction, JANUS, MAGIS, and UVS will construct a multi-wavelength depiction of 3I Atlas as it appeared on November 4th. We will acquire data spanning the spectrum from ultraviolet through visible and into the infrared. We will measure its composition, temperature, activity levels, and the spatial distribution of various materials. This will result in a data set that surpasses the capabilities of Earth-based observations. And this comprehensive data set will reside on hard drives for 3 months, awaiting downlink windows, entering processing queues, and gradually advancing through analysis pipelines, ultimately emerging as calibrated, validated, and publication-ready results in February. This will occur long after the observation itself, long after the moment when that information would have been most valuable. This is the inherent frustration of studying rare phenomena with spacecraft operating at great distances. Data is obtained, but not at the time it is needed. Answers are provided, but not when the questions are most urgent. Confirmation or refutation of hypotheses is achieved, but only after the focus of discussion has shifted to entirely different topics. By February of 2026, 3I Atlas will have become old news. The perihelion passage will be months in the past. The peak of speculation will have subsided. Individuals will have formed opinions, adopted stances, and decided upon their beliefs regarding this object. And only then will the JUICE data arrive, potentially challenging those positions, possibly necessitating a reassessment, or perhaps revealing that everyone was mistaken about a significant aspect. Alternatively, it might confirm what was widely suspected, demonstrating that 3I Atlas is indeed an unusual but natural comet, that all the observed anomalies have mundane explanations, that the initial excitement was exaggerated, and that we became enthused about something that proved to be ordinary once superior data became available. In either scenario, the JUICE observation represents a significant milestone, a crucial data point, one of the limited close-range measurements we will obtain of 3I Atlas during its passage. We should be appreciative that this observation is occurring at all, grateful that orbital mechanics aligned in such a way that a spacecraft was positioned to conduct these observations, grateful that ESA allocated resources to capture this data. However, gratitude does not diminish impatience. It does not alleviate the burden. It does not lessen the intense desire to know immediately, rather than in 3 months. It does not alter the reality that the information exists, has already been gathered, is stored in computer memory somewhere, and yet we cannot access it. We cannot even glimpse it. We cannot ascertain the slightest indication of whether JUICE observed anything noteworthy. November 4th arrived and subsequently passed. JUICE executed its planned observation sequence, directed its instruments toward 3I Atlas, collected photons, recorded spectral data, stored the gathered information, and continued with its mission. Somewhere within that stored data, lies a crucial piece of the truth, a measurement that will impart significant knowledge about the nature of 3I Atlas. We simply must await the revelation of what that knowledge entails. We must wait while the data traverses hundreds of millions of kilometers of empty space. We must wait while processing pipelines meticulously analyze the raw numbers and produce calibrated measurements. We must wait while analysts examine those measurements and decipher their meaning. We must wait while scientific papers are authored, peer reviews are completed, and press releases are drafted. 3 months, February of 2026. That is when we will receive answers from JUICE. That is when this particular segment of the puzzle will fall into place. Until then, it remains another item on the inventory of things we know exist but cannot access. Another tantalizing promise of forthcoming information. Another test of patience for everyone following this narrative. The spacecraft is functioning correctly. The data is securely stored. The data downlink will proceed according to schedule. All systems are operating as designed. The system is performing precisely as intended. And that system, despite its efficiency and reliability, imposes a 3-month delay between observation and disclosure. Thus, we wait again. We continue to perpetually await the next piece of information, the next data release, the next confirmation or surprise. Waiting has constituted the majority of our engagement with studying 3I Atlas, waiting for observations during periods of visibility, waiting for spacecraft to reach their observation positions, waiting for data to be processed, waiting for papers to be published, waiting for agencies to decide what information they are permitted to share. JUICE adds another item to this extensive waiting list. It adds another data point that we know is forthcoming but have yet to see. Another potential revelation or disappointment. Another opportunity for 3I Atlas to surprise us or to confirm our existing expectations. We will not know which until February. We will not know whether JUICE observed a comet or something else entirely. We will not know whether the November 4th observations lend support to the natural hypothesis or introduce new questions. The observation occurred. The truth has been recorded. We simply do not have access to it yet. The 8 anomalies, scaled rank 4. Let us now discuss the factors that differentiate 3I Atlas. This is not a matter of speculation or interpretation, but rather a presentation of measurements, documented observations, and verifiable facts accessible to anyone with access to the data. Specifically, there are 8 distinct ways in which this object deviates from what we would anticipate from a randomly encountered interstellar visitor. These are 8 anomalies that, individually, are improbable but not impossible. These are 8 data points that, when considered collectively, present a picture complex enough to warrant significant attention. Anomaly 1. Ecliptic alignment. 3I Atlas's trajectory lies within 5 degrees of the ecliptic plane. This is the flattened disk where planets orbit, the region where most solar system objects are concentrated, the area profoundly influenced by the gravitational forces and angular momentum originating from the primordial protoplanetary disk billions of years ago. Objects formed within our solar system tend to maintain orbits close to this plane. This is logically consistent as they coalesced from material that was already in a flattened disk configuration. However, 3I Atlas did not originate here. It arrived from interstellar space, from a different stellar system where the ecliptic plane would possess a completely different orientation. There is no inherent reason for an interstellar object to arrive aligned with our ecliptic. No physical mechanism exists that would preferentially direct objects toward us along that particular orientation. Random arrivals should originate from random directions, uniformly distributed across the celestial sphere. The statistical probability of a random alignment within 5 degrees is approximately 2%. This represents 2 chances in 1,000. While not impossible, nor even exceptionally rare, it is sufficiently unusual to warrant attention. It is unusual enough that if one were to observe 10 interstellar objects and find one aligned with the ecliptic, one would naturally inquire about the reason for this specific orientation. What sets it apart? Is there a discernible reason for its arrival from that particular direction? Anomaly 2. The anti-tail. We have previously addressed this phenomenon, the sunward-pointing plume that became apparent in early observations. This is a structure that did not conform to the expected characteristics of normal cometary tails. While anti-tails can indeed form, they are typically attributed to geometric illusions. However, this particular instance was not an illusion. It consisted of actual material demonstrably moving toward the sun, defying radiation pressure, solar wind, and the forces that are expected to propel all matter outward. Multiple telescopes corroborated this observation. Different viewing angles revealed the identical structure. It was not a matter of perspective, nor an artifact of the imaging process. It was genuine dust and gas exhibiting movement in the opposite direction of expected outward expulsion. This phenomenon necessitates an explanation. Natural explanations do exist, as we have observed. These include unusual sublimation dynamics, the behavior of ice fragments, and intricate interactions between different particle sizes and radiation pressure. Nevertheless, it remains anomalous. It represents something we have not previously encountered in quite this configuration. Anomaly 3. The timing. The arrival schedule that positions 3I Atlas in close proximity to multiple planets, while simultaneously rendering it unobservable from Earth during its perihelion passage. This includes an approach to Mars in October, proximity to Venus, an encounter with Jupiter in March, and its perihelion occurring during solar conjunction, a period when ground-based telescopes are unable to observe it. The probability associated with this precise timing is remarkably low, estimated at 0.005%, or 5 in 100,000. One could argue that this is a matter of selection bias. We tend to notice interstellar objects that pass close to planets because these are the ones sufficiently bright to be detected. Objects traversing the outer solar system, remaining distant from major celestial bodies, would likely go unseen. They would be too dim, too fast, and would depart before we were even aware of their presence. Therefore, it is plausible that the timing itself is not inherently unusual, but rather a consequence of our sampling only those interstellar visitors that happen to approach planets. This is a valid point, but it does not fully account for the perihelion occurring during solar conjunction. This alignment is independent of planetary positions. It pertains specifically to Earth's relative location to the object and the Sun, and for the optimal window for any potential maneuvers to coincide with a period when observation from Earth is impossible. That is indeed convenient. Suspiciously convenient. Anomaly 4. The chemistry. Nickel to iron ratios that bear a stronger resemblance to industrial alloys than to naturally occurring minerals. Specifically, the nickel to cyanide ratios are orders of magnitude higher than those observed in any known comet, including 2I Borisov, our sole other extensively studied interstellar comet. This chemical signature was the initial factor that attracted attention, prompting researchers to scrutinize the spectroscopic data more closely. Iron and nickel typically coexist. They are formed concurrently during stellar nucleosynthesis. They exhibit similar behavior during planetary formation processes. They condense from the solar nebula at comparable temperatures, meaning one would expect them to be present in roughly solar proportions, perhaps with some variation depending on the specific formation conditions. However, 3I Atlas displays a significant abundance of nickel with minimal iron present. This is an inverted relationship, contrary to what is typically produced by natural fractionation processes. Industrial alloys, conversely, are manufactured differently. We produce nickel steel. We refine nickel for specific applications. We create materials with ratios dictated by engineering requirements. If one were to examine debris from a satellite, remnants of a failed spacecraft, or material resulting from industrial processes, one might indeed encounter precisely this type of nickel-rich, iron-poor signature. While the presence of 8 peculiar characteristics doesn't definitively label 3I Atlas as artificial, it presents a collection of data points that deviate from typical natural expectations. Anomaly number 5, its remarkably low water content, is particularly noteworthy. The observed emissions indicate a mere 4% water by mass, a stark contrast to most comets, which boast significantly higher percentages. Water ice is the fundamental constituent of comets, the very element responsible for their characteristic sublimation, dust dispersal, and the formation of their coma and tail. Comets are commonly likened to dirty snowballs, primarily composed of ice with embedded rock and overwhelmingly water. However, 3I Atlas diverges from this norm. Its composition appears to be dominated by carbon dioxide, with water present but not as the primary component. It more closely resembles a rocky body adorned with surface ices rather than an icy sphere containing rock. This divergence could be attributed to genuine interstellar diversity. Variations in formation conditions within different stellar systems, perhaps a colder molecular cloud or a different chemical environment, could explain such differences. Given that we have observed only 3 interstellar objects thus far, a minuscule sample size, it's plausible that comets with low water content are prevalent in other regions of the galaxy. Alternatively, the bulk of the object might consist of rock or metal, with the observed ices being merely surface condensations. These ices might have accumulated over millions of years in interstellar space, forming a coating rather than constituting the main body. A mere 4 centimeters of ablation would be insufficient to ascertain what lies beneath, rendering it impossible to determine if the interior is composed of ice or an entirely different substance. Anomaly number 6, its extreme negative polarization, further fuels speculation. The light scattered from 3I Atlas exhibits polarization properties unlike any known comet. Polarization quantifies the orientation of light waves, indicating whether they vibrate in specific directions or randomly. When light interacts with particles, it undergoes polarization, with the degree and direction of this phenomenon contingent upon the particle's size, composition, and shape. 3I Atlas generates negative polarization exceeding any previously recorded for any comet, including Comet 2I Borisov. This suggests that the particles within its coma possess unusual characteristics, potentially related to their size, composition, or shape. The dust component exhibits properties that do not align with conventional cometary dust. The statistical likelihood of encountering such a distinct polarization signature is estimated to be less than 1%, implying fewer than 1 in 100 comets would display this trait. Once again, we confront the issue of a limited sample size. It's possible we simply haven't yet encountered a sufficient number of comets to comprehend the full spectrum of natural variations. Interstellar comets might inherently differ from those originating within our solar system. Formation within diverse stellar environments could result in dust particles with distinct properties. All these possibilities are viable and logical, yet the phenomenon remains anomalous and necessitates further investigation. Anomaly number 7 involves the alignment of the WOW signal. Tracing 3I Atlas's trajectory backward points towards a celestial region within 9 degrees of the origin of the renowned WOW signal. This radio signal, detected on August 15, 1977, consisted of 72 seconds of powerful, narrow-band emission that has never been conclusively explained, repeated, or attributed to any known astronomical source. The signal emanated from the direction of Sagittarius, generally towards the galactic center, an area densely populated with stars. Jerry Ammon, the astronomer who identified it in the data, famously exclaimed, "Wow," in the margin due to its exceptional strength, clarity, and precise characteristics, suggestive of an artificial transmission. Subsequently, it vanished, never to be detected again, despite decades of subsequent observational efforts. 3I Atlas's trajectory originates from a remarkably similar direction, merely 9 degrees away, VDJ, a close proximity on astronomical scales. This proximity raises the possibility of a connection. If the WOW signal were indeed a transmission from a probe, and if that probe were 3I Atlas, announcing its arrival before falling silent, the geometrical alignment would be plausible. The temporal aspect, however, presents a challenge. A discrepancy of 48 years exists between the signal's detection and the object's arrival. Yet, if the probe were still at a considerable distance and transmitted early in its solar system ingress, the numbers might potentially align. This line of reasoning remains purely speculative. Numerous natural explanations have been proposed for the WOW signal, and while 9 degrees represents a close proximity, it is not an exact match. The probability of a random alignment within 9 degrees is approximately 6%, UDJ, 6 in 1,000. While unlikely, it is not entirely extraordinary. Nevertheless, it adds another piece to the developing puzzle, prompting further contemplation. Anomaly number 8 combines its velocity and trajectory. 3I Atlas entered the inner solar system at a velocity of 44 kilometers per second, exceeding the speeds of both Oumuamua and 2I Borisov. Its motion exhibits a significant excess velocity relative to the local stellar rest frame. This speed, coupled with its ecliptic alignment and the timing of its planetary encounters, creates a specific arrival configuration with an extremely low probability when all these factors are considered collectively. Each individual element is plausible in isolation. Fast interstellar objects exist, ecliptic alignments occur, and planetary encounters are commonplace. However, the convergence of all these elements in a single object presents a statistical challenge, driving the probability low enough to necessitate an explanation. While any single anomaly could be attributed to chance, 8 anomalies begin to suggest a discernible pattern. This aligns with the point made by Avi Loeb. He is not asserting that 3 Atlas is artificial, but rather that its improbability score is sufficiently high to warrant serious consideration of the artificial hypothesis, demanding thorough investigation and the collection of all available data before the object departs the solar system, rendering the opportunity irretrievable. This represents a reasonable stance and exemplifies responsible scientific inquiry when confronted with unusual phenomena. The counterargument is equally valid. While 8 anomalies may seem substantial, we have only thoroughly examined 3 interstellar objects, constituting a sample size of 3. Our understanding of what constitutes normal for interstellar populations remains limited. We are comparing 3 Atlas to comets from our solar system, but this comparison might be fundamentally flawed. Interstellar objects could systematically differ from their solar system counterparts. What appears anomalous to us might be commonplace in other stellar environments. Furthermore, we are susceptible to observational biases. We can only detect objects that are sufficiently large, bright, and close for us to observe. This means we are sampling only a minuscule fraction of all interstellar visitors. The vast majority likely pass through undetected. Consequently, the objects we do observe may not be representative, potentially being selected specifically for their unusual properties that enhance their detectability. All these points are valid and underscore the need for caution when over-interpreting limited data. However, they do not negate the fact that 3I Atlas is unusual, nor do they erase the 8 measured anomalies or alter the statistical improbabilities. They merely provide context, reminding us that unusual does not automatically equate to artificial, and that extraordinary claims necessitate extraordinary evidence. On a 10-point scale, Loeb assigns 3I Atlas a rank of 4. This score, less than half, is far from definitive, but it is high enough to warrant attention. It suggests that prematurely dismissing it as obviously natural would be premature. It indicates that the hypothesis of a potential technological origin deserves investigation rather than ridicule. The scale is designed to be objective. Each anomaly is assigned a probability, and these probabilities are then combined to produce a quantitative score, not a subjective judgment. One may disagree with specific probability estimates, argue that certain anomalies should not be counted, or propose alternative statistical frameworks. However, the exercise itself cannot be dismissed as unscientific. It is explicitly scientific, aiming to quantify the object's unusualness relative to expectations. The conclusion is that it is quite unusual, not unprecedented, and not impossible to explain through natural means, but unusual enough to warrant our attention. It is unusual enough to make further data acquisition worthwhile, and unusual enough that opportunities for spacecraft to observe 3I Atlas should be prioritized. This is indeed happening. The JUICE mission has allocated resources for its observation, and the trajectory of the Europa Clipper intersects its ion tail. Ground-based observation campaigns are being coordinated across multiple continents, and the IAWN training exercise is focusing on it. Resources are being allocated, and attention is being paid. Despite public statements downplaying artificial hypotheses, the scientific community is treating 3I Atlas as significant. Their actions speak louder than their press releases. When missions are retasked, observation campaigns are organized, and papers are published. Analyzing every detail, it reveals the true assessment. This object matters. These anomalies matter. The 8 data points that propelled it to a rank of 4 on Loeb's scale are significant enough that individuals are dedicating their careers and resources to understanding them. Whether that understanding ultimately confirms a natural explanation or uncovers something more extraordinary remains to be seen. The data continues to accumulate, measurements are being refined, and the picture is gradually coming into focus. With each new observation and additional data point, the probabilities shift, and the anomalies are either explained or reinforced, causing the score to either decrease or increase. Currently, it stands at 4 out of 10. This is our current assessment, based on the measurements. 8 anomalies, 8 improbabilities, and 8 reasons to continue observing this object carefully as it traverses our celestial neighborhood and recedes back into the darkness between the stars. What lies ahead? From December through March, the narrative is far from over. 3I Atlas has not yet departed, nor has it concluded whatever purpose it may have had in visiting our solar system. Whether its journey is a natural gravitational passage or something more deliberate, the coming months will reveal information that the preceding months could not provide. we will obtain data that is currently impossible to gather, test predictions, resolve ambiguities, and potentially compel us to fundamentally reassess our understanding of this object. Mark December 19th on your calendars, as this is when 3 Atlas will achieve its closest approach to Earth. While not close by conventional standards, VOV-DJ, at 269 million kilometers, further than the Sun and even Mars at its closest point VOV-DJ, it will be nearer than it has been, or will be again as it journeys back towards interstellar space. This proximity is close enough for ground-based telescopes to provide their most detailed views of the object post-perihelion. This period represents a critical observation window, offering an opportunity for amateur astronomers to contribute meaningfully. Backyard telescopes, citizen science networks, and independent observers worldwide can direct their instruments towards the same target, gathering data that bypasses official channels and is not subject to filtering, management, or delays imposed by institutional review processes. If any unusual events occurred during perihelion VOV-DJ, if 3I Atlas released objects, altered its trajectory, or activated any systems VOV-DJ, December will likely reveal them. The object will be visible, well positioned in the sky, and sufficiently bright for moderately sized telescopes to capture detailed imagery. Thousands of observers will be scrutinizing it, comparing positional measurements, and searching for any deviations from predictions, seeking evidence of activity not exhibited by natural comets. This is when the whistleblower's prediction will be put to the test. Recall the claim made in December. Many home-based observers will see it all. If this statement holds any truth, if it is underpinned by genuine insider knowledge, December will be the time we discover whether the object, emerging from its blind spot, reveals what transpired during those concealed weeks. The prediction is specific enough to be falsifiable. If December arrives and 3I Atlas appears indistinguishable from a normal comet, with no unusual phenomena observed and independent observations perfectly aligning with gravitational predictions, then the whistleblower was either mistaken, deceptive, or misinformed, and that particular thread of speculation can be disregarded. However, if something unusual does manifest, if observers begin reporting anomalies, if positional measurements indicate trajectory deviations, or if multiple independent sources document the same unusual features, then we will face a significant challenge. In such a scenario, speculation would transition into evidence, and the possibility, previously dismissed as a conspiracy theory, would become a matter requiring serious investigation. The observational window extends beyond December. 3I Atlas will remain observable throughout the winter months for observers in the northern hemisphere, gradually fading as its distance increases and tracking becomes more challenging. Nevertheless, it will remain accessible to serious amateur equipment and, certainly, to professional observatories. The observation campaign will continue, and data accumulation will persist. Then, on March 16, 2026, there is the Jupiter flyby. 3I Atlas will pass within 54 million kilometers of the solar system's largest planet, a proximity close enough for NASA's Juno spacecraft to observe it. Jupiter's gravitational pull might perturb its trajectory in measurable ways, and if there are any active systems on the object, or anything drawing power or generating emissions, Juno's instruments should be able to detect it. Juno is equipped with sensors designed to study Jupiter's magnetosphere, measure radiation belts, and detect charged particles and electromagnetic fields. These instruments are sensitive and sophisticated, capable of detecting subtle signals amidst noisy backgrounds. If 3I Atlas is emitting anything at all, VOV-DJ, whether in radio, ultraviolet, or particle radiation, VOV-DJ, Juno is positioned to detect it. The infrared instruments are particularly intriguing. Juno's Jovian Infrared Auroral Mapper, GIRAM, can measure thermal emissions, detect heat signatures, and identify temperature distributions that reveal where energy is being generated or radiated. If something within 3i Atlas is producing heat, if active systems are operational, or if the object's thermal properties deviate from expectations for a passive body of ice and rock, GIRAM should notice. This observation has been officially recommended. Avi Loeb has strongly advocated for it, and Congresswoman Anna Paulina Luna has formally requested it from NASA. The scientific justification is clear. The Jupiter encounter represents the final opportunity for spacecraft observation before 3i Atlas exits the inner solar system. After March, it will head outwards, crossing the orbits of the outer planets and fading into the deep space background, becoming impossible to study in detail. Therefore, March marks the final opportunity. DJ. The ultimate exam. The last chance to gather close-range data with instruments capable of measurements beyond the reach of Earth-based telescopes. It is the final opportunity to either confirm or refute the hypotheses that have accumulated around this object. Post-March, we will be left to analyze the available data, draw conclusions from incomplete information, and accept that some questions may remain unanswered due to a missed window. This is unless Juno detects something extraordinary, something that necessitates follow-up and justifies the scrambling of resources for additional observations even after the object should have fallen off priority lists. This scenario is unlikely. Space missions operate under strict schedules, budgets, and competing priorities. Once 3i Atlas has passed Jupiter, it will cease to be of significant interest and will be considered old news. Resources will be redirected to newer targets, and attention will shift elsewhere. However, between December and March, we have a crucial window of opportunity. We have multiple observational periods, utilizing different assets with distinct capabilities. Each observation serves to constrain possibilities, and each measurement narrows the range of viable explanations. Every data point contributes to resolving the ambiguities that currently make interpreting 3i Atlas so challenging. The question of its trajectory will be definitively answered during this period. By comparing December observations with predictions, meticulously tracking its position, and measuring any deviations from purely gravitational motion, we will ascertain whether 3i Atlas maneuvered. The measurement itself is straightforward. The interpretation may be complex, but the data will be unambiguous. Either the object will be where gravity dictates it should be, or it will not. Positional measurements are inherently precise. If it remains on its predicted track, within acceptable measurement uncertainties, this will provide strong evidence against the artificial hypothesis. Natural objects adhere to gravitational paths and do not deviate or make course corrections. Discovering 3i Atlas precisely on its predicted trajectory would suggest that nothing unusual occurred at perihelion, bolstering the natural comet explanation and significantly lowering its rank on Loeb's scale. Conversely, if it is not where it should be, with a measurable discrepancy, that presents a different narrative. In such a case, the deviation must be explained. Solar radiation pressure affects trajectories, but its impact is calculable. Outgassing creates propulsive effects that can perturb orbits, but these effects are correlated with observed activity levels and should align with observations of coma brightness. Any deviation that cannot be accounted for by known forces becomes problematic, serving as evidence that an external influence affected the object's motion. This external influence could still be natural. It might involve outgassing from an event we failed to observe, pulsed jets resulting from rotation at an inopportune time for measurement, or variations in solar wind density creating unexpected drag. Natural explanations exist for almost any scenario. However, Some natural explanations are more plausible than others, requiring fewer assumptions and aligning better with the overall pattern of observations. If 3I Atlas exhibits trajectory deviations that necessitate significant force to explain VDJ, a force consistent with observed activity levels, VDJ, then natural explanations begin to strain, requiring multiple improbable coincidences to occur simultaneously, making them appear less probable than alternative explanations we have been hesitant to consider. The IAWN campaign will span this entire period, from November 27th through January 27th, involving coordinated observations from multiple sites, standardized measurements, and shared data protocols. This represents planetary defense infrastructure operating at peak capacity. Every telescope within the network will be trained on the same target, with every observation logged, cataloged, and made available for analysis. On paper, it is designated as a training exercise, a method for testing systems and procedures, and a rehearsal for a potential real threat. However, it is also an unprecedented observational campaign, representing the most intensive coordinated study of an interstellar object ever undertaken. The resources dedicated to this effort would not be justified by pure scientific curiosity alone. These resources make sense if there is genuine concern about the object and a real possibility that it is something other than what it appears to be. The campaign will generate a substantial volume of data, including positional measurements accurate to fractions of an arcsecond, photometry to track brightness variations, and spectroscopy to monitor compositional changes. All data will be time-stamped and georeferenced, feeding into databases accessible to multiple analytical teams. This exemplifies modern collaborative science and the proper method for studying something deemed sufficiently important to warrant dedicated resources. The results will eventually be published, following analysis, peer review, and the completion of institutional processes. By late 2026, research papers will be published and conference presentations will be made, with findings gradually disseminated to the public. We will learn what the campaign has uncovered, whether the intensive observations have revealed anything unexpected, and whether the training exercise has yielded results justifying the considerable effort invested. However, we will not suspend judgment or wait for official results to form opinions. The amateur community will also be observing, posting images, sharing measurements, and discussing anomalies. The internet operates independently of peer review, and social media disregards institutional timelines. If anything interesting emerges, if backyard telescopes capture evidence of unusual activity, that information will spread instantaneously. This has both positive and negative implications. Positive in that it prevents information control, but negative in that it facilitates misinformation. It is positive because it democratizes data access, but negative because it complicates verification. It is positive in that it promotes transparency, but negative in that it rewards sensationalism over accuracy. The widespread network of observation, while potent, is inherently disordered. It generates both meaningful signals and irrelevant noise at equal rates. Discerning one from the other necessitates a commitment of time and specialized knowledge that the majority of individuals do not possess. Consequently, we will likely be left with a muddled perception. A multiplicity of accounts will arise, each with competing interpretations. Some individuals who are observing will detect anomalies in every direction. Others will find absolutely nothing out of the ordinary anywhere. The largest segment will perceive ambiguous information that reinforces their pre-existing beliefs. And amidst all this background interference, gradually and progressively, a shared understanding will coalesce. This will not occur because anyone has definitively established anything, but rather because a sufficient quantity of independent observations will accumulate, making patterns evident, isolating outlier assertions and clarifying the most plausible interpretation, even if absolute certainty remains elusive. This is the practical reality of how scientific inquiry functions. It is not characterized by pristine experimental designs with rigidly controlled variables, but by opportunistic and untidy observations of natural occurrences that resist our desire for absolute clarity. We collect whatever data we can obtain. We scrutinize it with the utmost care. We endeavor to be forthright regarding any uncertainties, and eventually, we arrive at conclusions that are likely accurate, even if we cannot definitively prove their correctness. The object designated 3I Atlas will be examined through this lens, encompassing the disarray of December's observations, the methodical approach of the IWN campaign, the advanced technological capabilities of Juno's instruments, the earnest enthusiasm of amateur astronomers, and the rigorous methodology of professional scientists, all balanced by conjecture and precise measurement, hope and critical doubt. Somehow, from this complex confluence, we will ascertain the true nature of this celestial body, or at least its most probable identity, or at the very least, what it almost certainly is not. The schedule has been established. The periods designated for observation are known. The necessary resources are in place. All preparations are complete. Our sole undertaking now is to await the advent of December. We anticipate the emergence of 3I Atlas from behind the sun, revealing its appearance subsequent to its closest approach to the star. We await confirmation of any transformations and the unveiling of any unforeseen developments. We seek to discover whether the concealed weeks have yielded anything substantial that warranted concealment. The resolution already exists. Whatever transpired during the perihelion has already occurred. The current condition of the object is fixed. Its orbital path is determined. The evidence is presently in transit through space, carrying the factual account with it. We have simply not yet directed our attention towards it. We have not accurately pointed our telescopes with sufficient precision to discern what is factual from what is mere conjecture. However, this will soon change. December is approaching. The windows for observation are about to open. Data will begin to flow. Questions will start to receive answers. Not all inquiries will be resolved, nor will perfect clarity be achieved, but it will be sufficient to enable progress. It will be enough to adjust probabilities. It will be sufficient to determine whether 3I Atlas is genuinely extraordinary, or whether our fervent hopes, vivid imaginations, and the profound human longing to not be alone in the cosmos have imbued it with exceptional significance. The playbook of information warfare is evident here. There is a discernible pattern, a recognizable structure in the way information concerning 3I Atlas disseminates, or fails to do so. If one has observed numerous governmental responses to unconventional events and has studied the methods employed by institutions to manage public knowledge when the stakes are elevated, one begins to recognize the characteristic tactics, the predictable sequences of actions, and the telltale signs that indicate active management rather than passive reporting. 3I Atlas exhibits this very pattern. It may not be executed with flawless coordination, as might be expected in a genuine conspiracy, but it is sufficiently pronounced to warrant examination, comprehension, and recognition, enabling one to perceive it when it unfolds. The initial phase involves discovery and preliminary assessment. A celestial object appears, is detected by automated survey systems, and is flagged as anomalous. The data is then fed into databases, accessed by researchers, and initial analysis commences. This stage is characterized by openness and transparency. The discovery is officially announced through appropriate channels. The Minor Planet Center publishes the orbital parameters. Other astronomical observatories verify the detection. Nothing is concealed because no sensitive information has been identified at this point. It is merely another celestial body until closer inspection. 3I Atlas passed through this stage in a conventional manner. The announcement of its discovery occurred on the 1st of July. Subsequent observations confirmed its interstellar origin. Early scholarly papers noted its unusual luminosity and activity. All of this information was publicly available and accessible, disseminated through the standard channels that serve the astronomical community effectively. There were no indications of clandestine activity, no delays, and no signs of information manipulation. The second stage involves the recognition of anomalies. Someone observes discrepancies. The spectroscopic readings are peculiar, the trajectory is questionable, or the timing appears too coincidental. At this juncture, the flow of information becomes more intricate. Certain researchers begin to exercise caution regarding their publications. Some observations are postponed while teams work to validate unusual findings. Some data is shared privately before its public release. These actions are not necessarily sinister, but rather reflect scientists' prudence in making claims that might later require retraction. However, institutions begin to take notice. Space agencies commence monitoring the situation. Committees convene to discuss potential scenarios and appropriate responses. This is where the mechanisms of control are activated. This is not due to definitive proof of anything unusual, but because there is sufficient ambiguity to necessitate consideration of what would happen if the situation were to prove significant. What if the aberrant characteristics are genuine? What if public interest escalates beyond the capacity of conventional scientific channels to manage it? 3. IATLAS entered this phase in late July and August. Papers began to appear employing carefully worded language. Observed anomalies were described, but not necessarily interpreted as artificial in origin. Dr. Lowe commenced publishing his analyses. Other researchers began to offer counterarguments. The scientific discourse commenced simultaneously in both public and private spheres. Data continued to be disseminated, and observations were still shared, but a palpable caution emerged, reflecting an awareness that this object was generating interest beyond the typical scope of astronomical inquiry. The third stage is characterized by containment and review. This is where active information management takes place. It is not outright suppression or a cover-up, but rather a meticulous process of ensuring that all information proceeds through designated channels. The objective is to prevent the release of any inflammatory material without institutional sanction. When information is eventually made public, it is ensured to have been vetted, contextualized, and presented appropriately. The government shutdown provided an ideal pretext for this stage. NASA was unable to release data due to furloughs. China refrained from releasing images pending the completion of their analysis. The European Space Agency released limited observations that offered little substantive revelation. Each entity had valid reasons for these delays and procedural justifications for the unavailability of certain data. Nothing appeared suspicious because all explanations were mundane. Nevertheless, the outcome was the same as if it had been a coordinated effort. High-resolution images remained undisclosed. Spectroscopic details were scarce. Activity reports were vague. The most detailed observations, the measurements crucial for resolving key questions, were held in limbo, undergoing processing, review, and preparation for eventual publication. But not yet. Not while the object remained in the public eye and people were actively observing and speculating. This represents information warfare waged through bureaucratic channels, through the normal operations of institutional processes that can be deliberately slowed when convenient and expedited when desired. No direct order for a delay in release would be issued, as that would be obvious and documented, with the potential for leaks. Instead, review processes coincidentally extend beyond their usual duration. Data queues coincidentally become backlogged. The publication pipeline coincidentally experiences bottlenecks, all of which are explainable and defensible, resulting in the same outcome as active suppression, but without any of the associated risks. The fourth stage involves the establishment of a narrative. Once sufficient time has elapsed, and initial speculation has peaked and begun to subside, official information starts to be released. Papers are published, press releases are issued, and data becomes accessible. However, by this point, the narrative has been established, the interpretation has been fixed, and the framing is in place. When the high-resolution images eventually emerge, they will be accompanied by expert analysis, context, and explanations of what is being observed and why it is consistent with natural phenomena. The data will be factual and the images authentic, but they will be presented within an interpretive framework that guides public perception. This is not outright deception or crude manipulation, but rather a communication strategy. It is responsible science communication. One does not simply disseminate raw data to the public and allow them to draw any conclusions they may wish. Instead, context is provided, the meaning of measurements is elucidated, and interpretation is guided to prevent unwarranted conclusions. This is the practice of responsible institutions and the intended function of science communication. However, this also means that institutions exert control over the narrative. They determine which details are emphasized, which questions are addressed first, and which interpretations appear most reasonable to audiences lacking specialized knowledge. This control, even when exercised with benevolent intentions, shapes public understanding in ways that may diverge from what the data actually indicates. 3i Atlas has not yet fully advanced to this stage. We are still in the containment and review phase, awaiting official data releases and relying on limited information coupled with considerable speculation. However, when Stage 4 arrives, as papers begin to surface and press releases are issued and data becomes accessible, pay close attention to how it is presented. Observe what is highlighted. Note which anomalies are explained and which are minimized. Pay attention to whose interpretation becomes the prevailing view that is universally repeated. The fifth stage is the gradual decline of attention. Once the narrative is firmly established and the official interpretation is settled, public interest naturally shifts elsewhere. New stories emerge, and new astronomical discoveries are announced. Resources are redirected to different priorities. 3i Atlas transitions from a topic of widespread interest to one primarily for specialists, no longer gracing front-page headlines. The general public moves on, ceases to pose questions, and stops demanding answers, accepting the conclusion that was formulated during Stage 4. This stage has already begun. Evidence can be seen in media coverage patterns. 3i Atlas garnered significant attention in July and August, with every science outlet and space enthusiast following updates. However, by October, the coverage had diminished. Fewer stories were published, fewer updates were released, and public engagement waned. This decline is not due to a decrease in the object's inherent interest, but rather because the news cycle has advanced. Human attention is finite, and stories have life cycles. This particular narrative has reached its zenith. By the time definitive data becomes available, such as results from the JUICE mission in February or Juno observations analyzed in April, a majority of people will have forgotten their anticipation for answers. Most will have already formed their opinions and moved on. The data will be published, and scholarly papers will appear, but they will be read by specialists rather than the millions who watched with bated breath in July when every new image sparked widespread speculation. This is a natural progression, characteristic of how news operates and reflecting the rhythm of public attention in the digital age. There is nothing sinister involved, merely the reality that individuals cannot sustain prolonged focus on a single narrative indefinitely. Other events unfold, other mysteries emerge, and other questions demand consideration. Consequently, gradually, and almost imperceptibly, yesterday's pressing question becomes today's forgotten topic. However, this is what renders the playbook so insidious. If one wished to conceal something or to prevent public understanding of something genuinely extraordinary, direct suppression would be counterproductive. Classifying everything and refusing to comment would inevitably generate backlash, fuel conspiracy theories, and arouse suspicion. Instead, the more effective approach is to permit information to flow, albeit slowly, through official channels, subject to appropriate review, and framed with responsible context. One would then allow the news cycle to take its course, permitting public attention to naturally wane and letting the story age until public interest diminishes. Subsequently, when the definitive data is finally released, it would arrive in a context where few are paying attention. The limited number of specialists who do engage with it would be unable to generate sufficient public discourse to reignite widespread interest. Perhaps this is precisely what is occurring with 3i Atlas. The delays might be strategic, with the data being withheld until public attention subsides. Consequently, by the time answers are provided, the majority of people may have already settled on their beliefs and may not be sufficiently motivated to revise them based on new evidence. Alternatively, the delays could be precisely what they appear to be: normal bureaucratic processes, standard scientific caution, and the ordinary functioning of institutions that are simply slow due to their inherent nature. This would imply no underlying strategy, no coordination, and no discernible playbook, merely the cumulative friction generated by multiple organizations with differing priorities and procedures striving to perform their duties diligently. The truth likely resides somewhere between these two possibilities. Some delays may indeed be strategic, while others are genuinely procedural. Some data might be deliberately held for review, while some is simply caught in the standard publication pipelines. Some information may be carefully managed, while some is merely progressing slowly through bureaucratic channels. Distinguishing between these scenarios from an external perspective is nearly impossible. One can observe the effects and note the patterns, but determining the intent without insider knowledge is unfeasible. This is the inherent strength of the playbook. It functions effectively regardless of whether it is intentional or not, and irrespective of whether anyone is actively implementing it. This is because the natural operation of institutional information management closely resembles coordinated control. Bureaucratic delays appear identical to strategic holds. Normal review processes are indistinguishable from censorship. Without documentary evidence of intent, differentiation is impossible, and such evidence, if it existed, would be precisely what would be most meticulously controlled. So, where does this leave us? We are left observing patterns in information flow, noting discrepancies, and observing which data is released and which is withheld. We recognize the underlying structure, even if we cannot definitively prove coordination, and understand that the absence of information is itself informative. The delays convey a narrative. What remains unsaid often carries more weight than what is explicitly stated. The playbook exists. We can observe its effects in the way information concerning 3i Atlas has circulated over the past several months. Whether it is being consciously executed or is an emergent phenomenon rather than a designed one, remains unknowable. However, the pattern is undeniably present, sufficiently clear to be recognized and consistent enough to be mapped. Recognizing this pattern assists in understanding why certain data has not yet materialized, why particular observations remain unpublished, and why the story that seemed so urgent in July has gradually receded from public attention, despite the object being more intriguing now than it was then. The information warfare playbook accounts for these patterns, renders them predictable, and illustrates what to anticipate in the coming months as Stage 4 unfolds and Stage 5 takes effect. We are being managed. Our expectations are being shaped. Our comprehension is being guided, not through falsehoods or suppression, but through the strategic timing and framing of information dissemination, through the natural operations of institutions that understand communication strategy, and through processes that function identically whether they are consciously coordinated or simply structured organically. Perhaps this is appropriate. Perhaps the public genuinely requires guidance. Perhaps raw data devoid of context leads to greater confusion than clarity. Perhaps responsible institutions should indeed control the narratives surrounding potentially sensitive subjects. Perhaps information warfare is simply a more honest designation for effective communication. Conversely, perhaps we are entitled to unfiltered access to data. Perhaps we are capable of reaching our own conclusions. Perhaps institutional control, even when well-intentioned, is at best patronizing and at worst dangerous. This is a question of values, a political question, one that individuals will answer differently based on their preconceived notions about trust, authority, and the role of institutions in democratic societies. However, regardless of whether one deems the playbook appropriate, it exists. It is being enacted, and it is shaping what we know, when we know it, and how we interpret it. Understanding this, perceiving the structure, and recognizing the pattern grants us a degree of power, DJ. The power to question, the power to seek information in avenues where it is not readily offered, and the power to identify when we are being managed and to resist that management if we choose. The narrative of 3i Atlas is still in the process of being written. The concluding chapters have yet to transpire, but the informational infrastructure surrounding this story, the systems that dictate what becomes known, when it becomes known, and how it is conveyed, are fully operational. They were activated months ago and are functioning smoothly, performing precisely as they were designed to do. Whether this serves to protect us from premature conclusions or prevent us from reaching accurate ones, we will only ascertain in retrospect once it is too late to make a difference.